Hello there, and welcome to the Cosmographer. On a December night in 2020, the first close-up image ever taken of a star outside our galaxy came back the wrong shape, and nobody has explained it since. That star is number 6 on tonight's list. There are 9 others, and every one of them carries a question that is still open in the published literature tonight. Number 8 had 97% of its light removed for 200 days by something nobody has ever identified. Number 7 turns 707 times every second and weighs more than any neutron star ever measured. Number 3 is 100 young stars sitting in the one place in the galaxy where nothing can be born. Not one of these stars can ever be reached, and they are ranked by a single rule: how much of the star the mystery has eaten. Get comfortable and settle in. If you enjoy falling asleep to lists like this one, a quick like and subscribe helps this channel reach more curious minds like you. Because the star at number 1 is bright enough to find from a back garden with a small telescope, and it is the one we understand least. Let's begin at number 10. Number 10. The star that came out older than the universe. There are 2 rules holding this list together, and both of them are worth stating before we begin, because they will govern everything that follows for the next 3 hours. The first rule is that every star on this list has a real, open, unresolved question attached to it. Not a question that was answered 20 years ago and gets retold as a mystery. A question that is live in the published literature right now, argued about by people who have spent careers on it, and unresolved tonight. Where the argument has a winner, this video will say so. Where a claim has failed to be confirmed, this video will say that too. The second rule is that not one of these stars can be reached. Not by us, not by anyone we will ever build a vehicle for. Not on any timescale that means anything to a species. That second rule has a number attached to it, and the number is worth learning now, because we will come back to it at every single entry on this list. Voyager 1 is the fastest object human beings have ever thrown away from the Sun. It is moving at roughly 17 kilometers per second. At that speed, 1 light-year takes about 17,600 years. Hold that conversion. It turns every distance in this video from an abstraction into a sentence you can feel. The nearest star on tonight's list sits about 200 light-years away, and at Voyager speed, the trip takes 3.5 million years. That is the closest one. It gets worse. So the light is the only thing that ever makes the trip. Everything anyone has ever known about the 10 objects on this list arrived here as light, and nothing else ever will. That is not a poetic observation. It is the working condition of the entire field, and by the time we reach number 1, it will have become the whole point. Which brings us to the order. This list is not ranked by size, or by violence, or by how alarming an object sounds when you describe it. It is ranked by how much of the star the mystery consumes. At number 10, the mystery is a single number in a table, and the star itself is understood in almost complete detail. By the middle of the list, the mystery has grown to cover an event, then an interior, then a death. By the end, it has eaten the entire visible surface of a star. And every attempt to explain that surface either invents a companion nobody can find, or invents an element nobody has ever made, or concludes that a generation of careful people read the lines wrong. 10 stars. One rule for the ranking. Let us start where the mystery is smallest. Number 10 sits in the constellation Libra, close to the border with Ophiuchus, and it is catalogued as HD 140283. It has a nickname, which is where the trouble starts. People call it the Methuselah star. On paper, it is unremarkable in every way that matters. Visual magnitude 7.2, which puts it just outside what the unaided eye can see and comfortably inside what a decent pair of binoculars can. Its spectral designation is SDF3, and its physical state is that of a subgiant. The hydrogen in its core is finished. It has a dead helium core, it has swollen slightly, and it is on its way to becoming a red giant. Its radius, measured directly by interferometry, is 2.167 times the radius of the Sun, with an uncertainty of about 4/100ths. Its luminosity is about 4.5 times the Sun's. Its mass sits somewhere between 0.73 and 0.81 solar masses. Nothing there is strange. What is strange is that we have been looking at this star for over a century, and we still cannot agree, to within about 2 billion years, on when it was born. The story does not begin with a discovery. It begins with an escalation. In 1912, Walter Adams was working at Mount Wilson with a 3-prism spectrograph, and he flagged this star as the first high-velocity star he had seen whose spectral type was far too early for how dim it was. Something did not fit. He did not know what. Then, in 1951, Joseph Chamberlain and Lawrence Aller identified it as genuinely metal-poor. That sounds like a technical footnote, and it was one of the foundational moments of an entire field. Before that work, the idea that some stars simply contain far less iron than others was not established. This star helped establish it. It is deficient in iron by a factor of roughly 250 compared with the Sun. That deficiency is the key to everything that comes next, because in astronomy, low metal content means old. The universe began with hydrogen and helium, and almost nothing else. Every atom of iron in existence was manufactured inside a star and scattered by that star's death. A star with very little iron in it must have formed early, before very many stars had lived and died to enrich the gas. Measure how little iron a star has, and you have a rough clock. The problem is that a rough clock is not good enough for what this star was about to be asked to do. To get a precise age from a star like this, you need to know exactly how bright it truly is, which means you need to know exactly how far away it is. That is the whole game. And distance, for a nearby star, comes from parallax, the tiny apparent shift in a star's position as the Earth swings from one side of its orbit to the other. Howard Bond decided to measure it properly. Working with Edmund Neylan, Don Vandenberg, Gail Schaefer and Diane Harmer, he used the fine guidance sensors aboard the Hubble Space Telescope. Not the cameras. The guidance system, which is built to hold the telescope steady on a target, and which happens to be one of the most precise position-measuring instruments ever put in orbit. They observed this one star at 11 separate epochs, spread across 8 years, from August 2003 to March 2011, each observation timed for maximum parallax advantage. The result was a parallax of 17.15 milliarc seconds, with an uncertainty of only 0.14. The previous best measurement had an uncertainty 5 times larger. That put the star at 58.3 parsecs, which is 190.1 light-years. And when Bond fed that distance into stellar evolution models, the age came out at 14.46 billion years. The age of the universe, measured from the cosmic microwave background by the Planck satellite, is 13.787 billion years, with an uncertainty of 2/100ths of a billion. Bond's central value for this one star was more than 500 million years older than the universe that contains it. He knew, of course, that it could not be. He said so in the paper. The formal uncertainty on his measurement was 0.31 billion years from the parallax alone, and 0.8 billion once every systematic effect was folded in. 0.8 billion years of slack is enough to reconcile the numbers. But it is worth sitting with the shape of what happened, because it is the honest version of a headline that got told badly for a decade. Nobody found a star older than the universe. Somebody measured a star very carefully, and the answer landed in a place where the error bars were the only thing preventing a contradiction. Bond's error budget is the most interesting part of the whole paper, and almost nobody quotes it. The parallax contributed 0.21 billion years of uncertainty. The star's apparent brightness contributed 0.23. Interstellar reddening, 0.06. The star's surface temperature, 0.35. Its iron abundance, 0.10. The solar oxygen scale, 0.20. And the star's own oxygen abundance contributed 0.61 billion years, which is larger than every other term combined. Sit with that. The single largest source of uncertainty in the age of the oldest well-measured star in the sky is how much oxygen it has. Not the distance. Not the telescope. Oxygen. That is the first thing to understand about this entry, and it is the thing that makes it number 10 rather than number 20. The star is not strange. The record is really a statement about our instruments. Every number on this list is going to be some version of that, and this is the gentlest version there is. Then Gaia arrived, and the star moved. The Gaia spacecraft measured a parallax of 16.26 milliarc seconds, with an uncertainty of only 26 millionths of an arcsecond. That is a far better measurement than Hubble's, and it puts the star at 61.67 parsecs, or 201.2 light-years. Between one telescope and the next, the star retreated by about 11 light-years. 11 light-years is nothing on the scale of this video. It is the difference between a 3.35 million-year Voyager crossing and a 3.54 million-year one. But it is not nothing to a stellar model. Move a star farther away, and it must be intrinsically brighter to look the same, and an intrinsically brighter subgiant of that mass is at a different point in its life, which changes its age. And the age has been moving ever since, in both directions, and it has never stopped. In the year 2000, Don Vandenberg published an upper bound of 16 billion years. That, not Bond, is where the famous 16 billion year figure actually comes from. 2 years later, Vandenberg and colleagues published 13.5 plus or minus 1.5. Bond, in 2013, gave 14.46. Vandenberg again in 2014 gave 14.27. Creevy and colleagues in 2015, using interferometry, gave 13.7, or 12.2 if you allow a small amount of dust in the way. In 2021, Fan Tang and Meredith Joyce combined stellar models with measurements from the Cara interferometer array and got 12.0 billion years, with a mass of 0.81. That is more than 2 billion years younger than Bond's number for the same star. In 2024, a group at Liège did something clever. Instead of assuming the star's chemical mixture is a scaled-down copy of the Sun's, they built opacity tables, tailored element by element to what this star actually contains. On the standard treatment, they recovered about 14 billion years. On their tailored treatment, they got 12.6 to 13.1. One modeling choice, more than 1 billion years of difference. And then, in 2025, a team at Aarhus did something nobody had managed before. They detected the star ringing. Stars oscillate. Sound waves trapped inside them make the surface rise and fall by tiny amounts, and the frequencies of those oscillations depend on the interior structure in a way that models cannot fake. Using data from the TESS satellite at 20-second cadence, the team pulled out 6 radial modes and 11 dipole modes from this star. It is the first asteroseismology ever performed on it. The answer came back at 14.2 billion years, plus or minus 0.4. Back up again. Higher than Tang and Joyce, higher than Creevy, higher than the tailored abundance result, and still a few 100 million years above the age of the universe at face value. The same paper also found a solar mixing length for the star's convection, which directly contradicts the subsolar values the earlier analyses had needed. Nobody has yet combined tailored abundances with asteroseismology. When someone does, the number will move again. There are other things worth knowing about this star, while it sits at the bottom of the list. It still has its lithium at an abundance of 2.14, right on what astronomers call the Spite Plateau, which is close to the primordial flaw set in the first minutes of the universe. It has that lithium only because it has not yet reached the red giant branch. When it does, its outer convection zone will deepen, drag that lithium down into hot interior layers, and destroy it permanently. The clock is running on a measurement. It is also, almost certainly, not from here. When the Aarhus team computed its orbit around the galaxy for the first time, they found it moving on a highly eccentric, retrograde path, occupying the region in energy and angular momentum associated with a galaxy that the Milky Way swallowed between 8 and 11 billion years ago. Its magnesium, manganese, and aluminium ratios agree. This star was born somewhere else, in a smaller galaxy, and was taken. And its oscillations are peculiar in their own right. Its frequency of maximum power is 611.3 microhertz, which is the highest ever measured for any star this metal poor, and it sits 14% above what the standard scaling relation predicts. That discrepancy is unexplained. It is a small mystery living inside a bigger one. It moves at 361.3 kilometers per second relative to the Sun, which is the origin of the widely repeated figure of 800,000 miles per hour. It has no companion. Speckle imaging, a clean field around it, and its own well-behaved astrometry all rule one out. It is alone, it is passing through, and it has been measured by 4 generations of astronomers with progressively better equipment. And they still cannot agree, within 2 billion years, on how old it is. That is the smallest a mystery on this list ever gets. One number, on a star we otherwise understand completely, at 200 light-years, which is close enough that it is one of the 34 stars the Gaia mission uses as a calibration benchmark. We check other measurements against this one, and this one is still moving. The next star on this list was watched for 100 years by people who wrote down exactly what they saw and still could not say what it was, because the single measurement that explained everything was one nobody thought to make. Number 9. The star nobody could name for 100 years. Number 9 is catalogued as HD 45166, and it sits in Monoceros, the unicorn, a faint constellation wedged between Orion and Canis Major. It is 991 parsecs away, which is about 3,230 light-years. At Voyager speed, the crossing takes roughly 57 million years. Its apparent magnitude is just under 10, which means a modest amateur telescope will show it to you tonight as an unremarkable point of light. People have been photographing that unremarkable point of light since 1922. For 100 years, nobody could say what it was. The mystery at number 10 was one number attached to a star we understood. The mystery here is one property, and the property was invisible for a century because nobody performed the measurement that would have revealed it. That is a different kind of gap, and it is a slightly larger one, which is why it sits one rung higher on this list. Here is what the object actually is, now that we know. It is a binary. The ordinary half is a B7 main sequence star of 3.4 solar masses at 13,000 Kelvin, going about its business. The strange half is what astronomers call a quasi-Wolf-Rayet star, and it is the only one anybody has ever found. A Wolf-Rayet star is normally a monster. It is a very massive star that has blown its outer hydrogen away and is showing its bare, blazing core to the universe, usually with a wind pouring off it fast enough to strip a planet. Galactic Wolf-Rayet stars are typically 8 solar masses and upward. This one is 2.03 solar masses, with an uncertainty of 0.44. Its surface is at 56,000 Kelvin, roughly 10 times hotter than the Sun, and its radius is 0.88 times the Sun's, which is to say it is physically smaller than the Sun. 67% of its surface is helium. It rotates once every 124.82 days, which is remarkably slow for something that size. And the whole system is only about 105 million years old. So it looks like a Wolf-Rayet star, and it weighs almost nothing. That combination is what defeated a century of astronomers. The first serious description came from Carlota Anger, working at Harvard in 1933, using plates taken between 1922 and 1933. She wrote down what she saw honestly. The helium line at 4,686 angstroms was always present. The nitrogen lines came and went. She proposed a nitrogen sequence, Wolf-Rayet star, which was a reasonable reading of the evidence in front of her. What followed was a parade of contradictory labels that reads, in hindsight, like a field politely arguing with itself for 50 years. In 1948, it was classified W7N. In 1955, it was called BPE, a peculiar B star with emission. In 1956, William Hiltner described it as an O9 spectrum with high excitation lines pasted on top, and in the same work found the companion for the first time. In 1961, Ross searched for photometric variation and found none at all, which only deepened the problem. In 1968, it was called a Wolf-Rayet again. The term quasi-Wolf-Rayet, which is what the object is known by today, comes from a paper by Sarah Heap and Lawrence Aller in 1978. That paper was never actually published. The category the star belongs to originates in a manuscript that does not exist in the literature. In 1983, Alan Willis and David Stickland looked at ultraviolet data and argued that it was not a Wolf-Rayet at all, but a subdwarf O star of half a solar mass. That is a factor of 4 below the current best estimate, in the other direction. And between the 6th catalogue of Wolf-Rayet stars in 1981 and the 7th in 2001, HD 45166 was simply deleted. Its category, which had exactly 2 members, was abolished. The star was removed from the list of things it had been assumed to be, and no new list was offered. The best pre-modern work on it came in 2005 from João Steiner and Alexandra Oliveira, and it deserves a moment because of how it was done. They were trying to find an orbital period, which meant measuring the star's velocity along our line of sight to a precision far beyond what their spectrograph could formally deliver. Their instrument's resolution element was 6.2 kilometers per second. They achieved a precision of 0.2 kilometers per second. 30 times better than the resolution of the instrument they were using. They did it by treating the spectrum as a ruler with fixed marks on it. Oxygen in Earth's own atmosphere imprints absorption lines on every spectrum taken from the ground. Interstellar sodium sits between us and the star and does not move. Those features are stationary by definition, so any shift measured against them is real. The technique was so precise that gravitational redshift, the tiny stretching of light climbing out of a star's own gravity, had to be entered into the error budget of a measurement made on a 1.5-meter telescope. They found a period of 1.596 days, derived a mass of 4.2 solar masses, and computed an orbital inclination of 0.77 degrees, which would be one of the smallest orbital inclinations ever claimed for anything. It was careful, honest, elegant work. It was also wrong, and the reason it was wrong is the whole story. Thomas Schennar, then at the Anton Pannekoek Institute in Amsterdam, has described the moment plainly. He was reading through the accumulated literature on this star, 100 years of people describing something they could not classify, and a thought arrived. What if the star is magnetic? Nobody had checked. Measuring a magnetic field on a star requires a specific instrument, a spectropolarimeter, which measures not just the wavelength of light, but its polarization. Magnetic fields split spectral lines into components with different polarization states, an effect discovered by Peter Zeeman in the 1890s. If the field is strong enough, the split is wide enough to see directly. Nobody had pointed such an instrument at this star. On the 17th and 19th of February 2022, Schennar observed it with the Espadon spectropolarimeter on the 3.6-meter Canada-France-Hawaii telescope, taking 32 spectra at a resolving power of 65,000. He sent them to Greg Wade at the Royal Military College of Canada, who has spent his career on stellar magnetism. Wade's reply, as Schennar has recounted it, was that whatever this thing was, it was definitely magnetic. The full analysis pulled in everything anyone had ever taken. 36 archival spectra from the 1.52-meter telescope at La Silla from January 2002. 103 spectra from a 1.6-meter telescope in Itajuba, Brazil, spanning 1998 to 2004. 28 more from Mercator. Archival ultraviolet data. Photometry from the TESS satellite. 24 years of baseline and 199 separate velocity measurements, assembled around 2 nights of new observing. The field came out at 43,000 Gauss. That number needs a comparison, because 43,000 Gauss is meaningless on its own. 43 kilogauss is 4.3 Tesla. A hospital MRI scanner runs at 1.5 to 3 Tesla, so this is about 2 MRI machines. It is roughly 100,000 times the strength of Earth's magnetic field at the surface. Laboratory magnets have beaten it, and comfortably, physicists run continuous fields of 45.5 Tesla and pulsed fields around 100. The difference is that those fields exist inside a machine the size of a room, for seconds or minutes, at enormous cost. This one is held across the entire surface of a star, continuously, and has been for millions of years. And it was not inferred. It was measured directly from the resolved splitting of 2 oxygen lines, giving 44.1 kilogauss at one wavelength and 41.8 at another. The mean longitudinal component came out at 13.5 kilogauss, and the ratio between the two is exactly what you would expect from a simple dipole seen close to its magnetic pole. It broke a record that had stood for 63 years. The previous holder, Babcock's star, was measured at roughly 34 kilogauss in 1960. The previous record for a genuinely massive star was about 20 kilogauss, less than half. Finding the field also demolished the orbit. That 1.596-day period Steiner and Oliveira had found so carefully turned out not to be an orbit at all. It was pulsation in the ordinary B7 companion, non-radial waves rippling across its surface, confirmed independently by TESS photometry. The real orbital period is 8,200 days, which is about 22.5 years, on an eccentric orbit with a semi-major axis of 10.5 astronomical units. The system is far wider and far slower than anyone had thought. There are stranger details still. That 5-hour periodicity in its carbon lines has persisted, on and off, for at least 20 years, and nobody has explained it. The star is wildly luminous in X-rays, with a plasma component sitting at 70 million Kelvin and a directly detected ion signature, while being completely silent at radio wavelengths. And the magnetic confinement is so extreme that only about 6% of the star's wind ever escapes at all. The rest is caught by the field, held, and falls back. That is why its emission lines are narrow, 300 to 400 kilometers per second across, when a classical Wolf-Rayet has lines thousands of kilometers per second wide. The narrowness is the visible fingerprint of a wind that cannot get out. Which leaves two questions, and neither is settled. The first is where the field came from. Chenard, with Pablo Marchant, Norbert Langer, and Sylvia Thunen, proposes a merger. Not a merger of two whole stars, but of the helium cores of two intermediate mass stars inside what used to be a triple system, an inner pair of 5 and 3 solar masses orbiting every 2 days, with the B7 star we still see orbiting further out. Mass transfer, then reverse mass transfer, then a common envelope phase at 130 million years, and out the other side comes a magnetized 2 solar mass helium star at 133 million years, which matches the age of the companion. They rule out ordinary single-star stripping because that would need a progenitor that only lives 30 million years, and they rule out a white dwarf merger because those products explode within about 10,000 years. In 2025, an independent measurement using the gravity interferometer supported them. By resolving the binary directly, that team measured the closest approach of the two stars at about 7 astronomical units, and at that separation, an 8 solar mass progenitor could never have filled its Roche lobe. Binary stripping is excluded by geometry. The merger picture is the one left standing. Its own authors name its weakness. The merger model predicts a surface carbon abundance that does not match what is measured. Their proposed patch is contamination by material that fell back after the merger. That patch has not been tested. The second question is, what happens next? And here the field is arguing with itself so thoroughly that Chenard is a co-author on every side of it. The 2023 paper calls the star an immediate progenitor of a magnetar, while conceding that the final outcome depends on modeling uncertainties. The 2025 interferometry paper says the outcome could be an oxygen-neon-magnesium white dwarf or an electron capture supernova, and cites theoretical work questioning whether helium stars of this mass collapse at all. A separate 2025 X-ray paper comes down hard for the magnetar, on the grounds that the star's wind is so feeble that stripping it below the mass limit would take 500 million years, against a few million years of helium burning remaining. The entire question hinges on one number: 2.03 solar masses, plus or minus 0.44, measured against the Chandrasekhar limit of 1.44. If the mass is at the top of its range, this star collapses. If it is at the bottom, it cools quietly into a white dwarf, and nothing happens at all. Those are two completely different futures, and the error bar covers both. And nobody can go and check. That phrase is worth remembering because it is going to come back near the end of this list in a much heavier form. The measurement cannot be improved by thinking harder. It can only be improved by more observing on a system whose next genuinely new data point, the next close passage of the two stars, falls around the year 2040. If it does become a magnetar, one number is worth carrying with you. Take that 43,000 Gauss field and compress the star that holds it down to a neutron star 12 kilometers across. Magnetic flux is conserved. The field strength that comes out the other side is roughly 100 trillion Gauss. The field we are calling a record today would be the seed of something 2.3 billion times stronger. The models go further than that, and the detail is worth having. If this star does collapse, it does not simply fall over. It first swells into a supergiant roughly 300 times the radius of the Sun, which is a strange thing for an object currently smaller than the Sun to do. Then it detonates as a relatively modest supernova, driven by electrons being crushed into a core of oxygen, neon, and magnesium weighing about 1.29 solar masses. What is left is a magnetar spinning about once every 40 milliseconds, which is close to the rotation rate of the pulsar at the heart of the Crab Nebula. That is fast, but it is not fast enough to power anything exotic. The models are clear that there is not enough rotational energy there for a superluminous explosion or a gamma-ray burst. It would be an ordinary catastrophe with an extraordinary object at the center of it. There is one more consequence, and it closes a loop nobody was looking to close. The kick delivered by that explosion would tear the binary apart, throwing the two stars away from each other permanently. Which fits an observation that has puzzled people for years. Every single magnetar known in the Milky Way is isolated. None of them has a companion. If magnetars are made this way, the reason they are alone is that the act of becoming one ends the marriage. Julia Bodensteiner, one of Chenard's co-authors, gave the object a nickname among the team. They call it the zombie star. A stripped core, still burning, long after its outer body was taken away. It is worth noting how far the estimates have traveled. Published masses for this one object over 90 years have run 0.5, then 4.2, then about 4, then 2.03, then 1.96 solar masses. A factor of 8 on the same star by careful people using the best instruments of their day. Chenard has made one prediction that is easy to test and has not yet been tested. He suspects other massive magnetic helium stars have already been catalogued, sitting in the Wolf-Rayet lists right now, misfiled for exactly the same reason this one was, because nobody has pointed a spectropolarimeter at them. A star observed for 100 years, described accurately every time, and never once understood, because the right instrument was never aimed at it. At least it can be watched. The next star on this list spent about 200 days almost entirely switched off, and nobody on Earth noticed for 9 years. Number 8, the giant that blinked. The designation of number 8 is a confession, and once you know what it stands for, it is hard to read it any other way. The object is catalogued as VVV-WIT-08. The first part is the survey that found it. The middle part, WIT, stands for What is this? It is the label the survey attaches to objects it cannot classify at all, and this is the 8th of them. It sits at 18 hours right ascension, minus 30 degrees declination, in Sagittarius, which means it sits almost exactly down the barrel of the galactic bulge. Everything in that direction is crowded, dusty, and hard. The star itself is a cool giant, no earlier than spectral type K7 and no later than M2, with a surface temperature of 3,614 Kelvin and a metal content slightly below the Sun's. A weak molecular band in its spectrum rules out its being a supergiant. In the infrared, it sits at magnitude 11.5. In visible light, about 14.7. In 2012, 96.93% of its light went away. Not a dip. Not a flicker. Almost all of it. The minimum fell on the 4th of April 2012, and the event lasted somewhere between 170 days and a few hundred, depending on which end of the light curve you measure from. The paper's own introduction says approximately 200 days. Then the light came back, and the star has been perfectly steady ever since. 17 years of survey coverage on this object. Exactly one such event. At number 10, the mystery was one number. At number 9, it was one property. Here the mystery is one event, an event with a beginning and an end, entirely in the past, entirely recorded, and entirely unexplained. The distance is its own problem, and it is worth being honest about, because the popular coverage was not. We do not know how far away this star is to within a factor of 3. Its measured parallax is 9,000ths of a milliarc second, with an uncertainty of 74 thousandths. In plain terms, the measurement is consistent with 0, and therefore carries no information. So the team did what you do when you have no parallax. They estimated the distance 2 different ways, and got 2 answers that will not sit together. Match the star's motion across the sky to a model of how bulge stars move, and it lands between 6 and 13 kiloparsecs. That is roughly 20,000 to 43,000 light-years. But then its radius comes out at about 31 times the Sun's, and its mass at about 4/10ths of a solar mass, which makes it underluminous for a normal giant. That does not fit. Fit stellar isochrones instead, matching its colors and temperature to a track, and it lands at 19.9 kiloparsecs, about 65,000 light-years, with a radius 69 times the Sun's, and a luminosity 700 times the Sun's. That fits a normal giant. But then its sideways velocity comes out at about 493 kilometers per second, which is halo-like, at or above the speed required to escape the galaxy entirely, and that sits badly with a star carrying this much metal. The team refused to choose. They call the first set sensible lower limits, and the second set sensible upper limits, and say the truth is somewhere in between. That is the correct answer, and it is an uncomfortable one. At Voyager speed, the near solution is a 350 million year crossing, and the far solution is 1.15 billion years. We do not know which. The discovery was an accident, twice over. The survey is called VVV, the Variables in the Via Lactea Survey, together with its extension, and it runs on the Vista telescope in Chile, operated by the European Southern Observatory. Between 2010 and 2019, it sampled more than 1 billion individual sources in the infrared, repeatedly, looking for anything that changed. This object surfaced once, during validation of a preliminary light curve database, and independently again during a search for objects that had varied by more than 4 magnitudes. The optical side came from the OGLE survey, run out of Warsaw, which has been monitoring the same part of the sky since 2001. Their standard pipeline could not handle this event. A brightness swing that large breaks the assumptions built into automated photometry, so the light curves had to be completely re-reduced with new templates and image subtraction before anybody could trust a single point in the dip. The work was led by Lee Smith at the Institute of Astronomy in Cambridge, with Sergei Kopasov, Philip Lucas, Dante Miniti, Andrei Udalski, Pavel Pietrukovich, Valentin Ivanov, and Roberto Saito among the authors. It was published in June 2021. 9 years after the star went dark. Consider what that means. On the night of the 4th of April 2012, a red giant that had been shining steadily for something like 1 billion years had almost all of its light removed. The Milky Way that night was where it always is, a wall of stars low in the southern sky. Somewhere in that wall, at a position nobody on Earth was watching in particular, the deepest known eclipse of its kind was reaching its floor. The Vista telescope recorded it, because Vista records everything in that direction as a matter of routine. The file went into an archive. There was no alert. No astronomer looked up. No alarm sounded anywhere on the planet. The star finished its event, brightened back to normal over the following months, and returned to being one of 1 billion catalogue entries. 9 years passed. Somebody opened the file. That is the shape of the modern sky. The instruments see far more than the people do, and the gap between the seeing and the noticing is measured in years. Now, the physics, which is where it becomes properly interesting. The single most important fact about this event is that it was achromatic. The star dimmed by almost exactly the same fraction in visible light as it did in the near-infrared, across a wavelength range from about 0.5 micron to 2.2 microns. The visible measurement matched the infrared model within the errors. At the very deepest point, the infrared sat 20 or 30% below the model, but that residual is about 1% of the star's normal brightness, and it returned to prediction on the way out. Dust does not do that. Dust scatters blue light more efficiently than red, which is why sunsets are red, and why every dusty object in astronomy reddens the light behind it. Whatever passed in front of this star treated every color identically. That means it was optically thick, effectively solid as far as light is concerned. And it was enormous. To produce a dip that deep, over that long, the occulta must be at least 1/4 of an astronomical unit across, which the paper restates as a conservative minimum of 50 times the radius of the Sun. Whatever it was substantially larger than the star it hid. It also was not round. The team tried fitting a solid sphere on a straight-line path and got what they describe, with admirable restraint, as a mediocre fit. To reproduce the actual shape of the light curve, the occulta has to be elliptical in projection. Either it is genuinely elongated, or it is a disk seen very nearly edge-on, so that what we are calling its minor axis is really its thickness. So, something at least 50 solar radii across, opaque at every wavelength, elongated, moving at a few to about 10 kilometers per second relative to the star, invisible before the event and invisible after it. The elimination is thorough, and it is worth walking through, because the value of this entry is watching a competent team fail honestly. Could the star have done it to itself? No. There is no known stellar mechanism that removes 97% of a star's output uniformly across that entire wavelength range. Stars that soot up their own atmospheres, the R Coronae Borealis variables, dim far more deeply in blue than in red, and show excess mid-infrared emission from the soot. This star shows neither. Could it be a young star still wrapped in its birth material? No. The spectrum is wrong. There is no star formation anywhere nearby, and young star extinction is not achromatic. Could it be a chance alignment with some random dark object drifting past? The team ran the numbers. A population model of that direction predicts 18 such events across the whole survey, but only if dark occultas were as common in the galaxy as stars are. they are not. So it has to be a companion orbiting the giant. And then every candidate companion fails. A disk around a young stellar object has roughly the right size, but at these distances, the system would sit more than 400 parsecs above the galactic plane, and the clouds that make young stars have a scale height of 35 to 50 parsecs. It would be in the wrong place by an order of magnitude. A debris disk, of the kind that surrounds many normal stars, is optically thin. It could not block the light. A debris disk around a white dwarf has exactly the right physics and entirely the wrong size. Those disks are truncated near one solar radius. We need 50. An accretion disk around a black hole or neutron star would need a compact object of 10 to 50 solar masses to be that large, and such a system should be a source of X-rays. There is no X-ray source within 2 arc-minutes of this star. A hot subdwarf wrapped in an opaque disk is the closest published analog, and it is the accepted solution for another object we will come to in a moment. But forming a hot subdwarf requires mass transfer away from the giant, which strips the giant, which makes the already awkward too small radius problem worse. A disk made of materials stripped off the giant itself is, in the team's own word, attractive. It would explain the size, and it would fix the radius problem at the same time. The difficulty is that the giant currently comes within only about 10% of filling its Roche lobe. It is not spilling material now, so the disk would have to have been built earlier, and the orbit would have to have migrated outward since. Exactly one candidate survives without an immediate objection, a fallback disk around a black hole, a structure made from material that failed to escape when the star that formed the black hole exploded. The abstract's own verdict is that none of these are completely satisfactory matches to all the data, and that the object's secret has still not been fully revealed. Sergei Kopasov summarized it publicly with a sentence that does not try to be more than it is. They observed a dark, large, and elongated object pass between us and a distant star, and they can only speculate about its origin. The orbit is the last thing worth pinning down, and it depends on the distance, which we do not have. Fitting the shape of the dip gives a relative velocity between star and occulta of about 5 kilometers per second on the near-distance solution, or about 10.5 on the far one. Convert those into orbital periods, and you get either 242 years or 23 years per solar mass in the system. So the honest statement is this: the thing that hid this star will come round again, and it will do so either within a human lifetime or roughly 3 lifetimes from now, and nobody can currently tell you which. If it is the shorter figure, somebody alive today will see it happen. If it is the longer one, the next observation of this event belongs to people who have not been born. There is a second anomaly hiding inside the first, and the team names it. If this giant is on an ordinary single-star evolutionary track, then it has an unusually large space velocity. If it has a typical velocity and distance for its direction, then it has an unusually small radius. You cannot have both. Their attempt to find a binary evolution model that produced a star like this was, in their word, fruitless. Some smaller details, which accumulate into a kind of portrait. The only spectrum anyone has of this object came from a single night, the 4-meter SOAR telescope, on the 22nd of June, 2019, during commissioning tests of a new infrared spectrograph. Out of eclipse, the star shows weak quasi-periodic variability at about 195 days and about 124 days, which is uncomfortably close to the duration of the dip itself, and say mean nothing at all. There is no ultraviolet detection. There is no mid-infrared excess. 3 neighboring stars within 2 arcseconds on the sky did not dim, which is how the team ruled out anything atmospheric or instrumental. And the long ogle baseline rules out any orbital period shorter than about 11 years, which means we will not see this again soon. The modeling was so difficult that including the parallax as a free parameter defeated every statistical sampler they tried, even after they modified the sampling software themselves. In the end, they simply removed the parameter. The other objects in the What Is This file are worth a moment because they show how routine the unexplained has become. Number 1 was probably an obscured nova, or possibly two protostars colliding. Number 4 turned out to be a violently variable quasar, seen straight through the disk of our own galaxy. Number 6 was a nova, or a stellar merger. Numbers 10 and 11 are still unclassified, and number 11 vanishes completely for an entire observing season at a time. Number 7, in Scorpius, is the closest sibling to tonight's entry. It shows recurring dips, including a very deep one in July 2012, dimming by up to about 80%, with an infrared spectrum so featureless that it tells you almost nothing. And then there are the two established cases that make this look like a class rather than a freak. Epsilon Aurigae is eclipsed every 27.1 years by a disk surrounding a hidden companion. It was first noticed to be variable in 1821, and during the 2009 to 2011 eclipse, interferometry actually imaged the disk in silhouette crossing the star's face. And a fainter object in Taurus holds the record, a red giant eclipsed every 69.1 years by a disk around a stripped companion, with each eclipse lasting 3.5 years and removing 4.5 magnitudes of light. Its orbit was reconstructed from more than 120 years of archival photographic plates. Its next eclipse begins in April 2080 and ends in September 2083. That is the team's actual claim, and it is bigger than one star. They argue these objects may point to a broad class of very long-period eclipsing binaries in which a giant star is periodically hidden by a disk around a companion nobody can see. About half a dozen members are known. The Vera Rubin Observatory, which will photograph the entire southern sky every few nights, is expected to find many more. But that is the class. This particular object remains what its name says it is. Something large and dark passed in front of a red giant, took away almost all of its light for most of a year, and left no other trace of itself in any wavelength anyone has looked at. The next star on this list leaves a trace constantly. It is the loudest object we have met so far, and it is still less understood than any of them, because its mystery is not something orbiting the star. It is inside it. Number 7, the Black Widow. Number 7 is in Sextans, a small and unglamorous constellation just south of Leo. It is catalogued as PSRJ 0952-0607, and it is spinning 707.31 times every second. That number deserves a moment before anything else. 707 rotations per second means one full turn every 1.41 milliseconds. A kitchen blender at full speed manages about 600 turns per minute. This object does more than that in a single second. The object doing the turning is roughly 12 kilometers across and weighs more than the Sun, which means its equator is moving at something like 50,000 kilometers per second. Around 18% of the speed of light. A surface made of matter, moving that fast and holding together. We are moving up the list now, and the reason this sits above the blinking giant is a change in where the mystery lives. At number 8, something passed in front of a star, and we could not identify it, but the star itself was ordinary. Here, the object is not ordinary anywhere, And the unresolved question is not about anything orbiting it. It is about what it is made of, in the middle, at a density no laboratory on Earth has ever produced or ever will. First, the distance, because this one needs care, and the press got it badly wrong on the day. Pulsar distances are usually estimated from dispersion. A radio pulse traveling through interstellar space is slowed slightly, and the slowing depends on wavelength, so the low frequencies arrive after the high ones. Measure that delay, assume a model of how electrons are distributed through the galaxy, and out comes a distance. There are two standard electron models in wide use, and for this object, they disagree with each other. One gives about 3,160 light-years, the other about 5,675. But modeling the light of the companion star gives a very different answer: 6.26 kiloparsecs, or about 20,400 light-years. And the team that did that work concluded flatly that both electron models are overestimating the electron density along this particular line of sight. Forcing the nearer distance would require the companion to have a density above 100 grams per cubic centimeter, which is higher than any other object of its kind. There is no parallax for this pulsar. There is no independent check. On the day the mass result was announced, one press release said 3,000 light-years, and another, from a different observatory, said 20,000. The second is the one that matches the paper. 20,400 light-years is a Voyager crossing of about 360 million years. It is a useful reminder that a distance in astronomy is very often a modeling result wearing the clothes of a measurement. It was found on Christmas Day, 2016, in a single 20-minute observation. Cees Basser at the Astron Institute in the Netherlands, working with Jason Hessels, René Breton, Lars Nieder, Colin Clark and others, was hunting for pulsars in an unusual way. The Fermi Gamma-ray satellite has catalogued a great many sources of high-energy photons that are not associated with anything known. Some fraction of those are millisecond pulsars. The team was picking targets with the right fingerprint, a gamma-ray spectrum peaking around 1.4 giga-electronvolts, a small position uncertainty, and a location well away from the galactic plane. Then, instead of using the frequencies pulsar searches normally use, between 300 MHz and 3 GHz, they used LOFAR, the low-frequency array, at 135 MHz. Far below the standard band. They used the innermost 21 core stations, formed 7 beams on the sky, and in one 20-minute pass, the pulsar showed up blindly, at high significance, in 4 of those 7 beams. The reason it had been missed is now obvious in hindsight. Its radio spectrum is one of the steepest ever measured, which means it is bright at low frequencies and faint at high ones. Every high-frequency survey that had covered that patch of sky had walked straight past it. It took an instrument built to look at the wrong end of the spectrum, pointed at a gamma-ray source, on a public holiday. The optical counterpart was pinned down at the Isaac Newton telescope on La Palma in January 2017. It varies by 1.6 magnitudes over a single orbit, which is a factor of more than 4 in brightness, every 6 hours and 25 minutes. That variation is the entire reason we know anything else about this system, so it is worth understanding. There are 2 objects here. One is the pulsar. The other is a companion of 0.032 solar masses, which is about 33 times the mass of Jupiter. It orbits every 6.42 hours, and it is tidally locked, which means the same face is turned toward the pulsar forever. There is no rotation, no day, no night that arrives. There is a permanent day side and a permanent night side, and a fixed line between them. The night side sits at 3039 Kelvin, glowing dull red on its own account. The day side is heated to roughly 6,200 Kelvin, which is hotter than the surface of the Sun. The difference across that fixed boundary is about 3,100 Kelvin. Stand on that boundary line. Behind you is a permanently dark hemisphere at the temperature of a dying ember. In front of you is a hemisphere held at a temperature the Sun's own photosphere does not quite reach. Above you, filling a fixed position in a sky that never turns, is a thing 12 kilometers across, closer than the Moon is to us, spinning 700 times a second. It does not look like a star. It is a strobe far too fast for any eye to resolve, and what it delivers is not warmth, but a wind of particles moving at nearly the speed of light. Under your feet, the ground is being lifted away, steadily, and carried off. The object is 33 Jupiter masses now. It used to be much more. About half of the pulsar's entire rotational energy loss goes into cooking that one companion. About half of 1% goes into the gamma rays by which the whole system was found. Now, the two records. The first is the spin. 707 Hz makes this the fastest spinning neutron star anywhere in the field of our galaxy, and the second fastest known anywhere at all. Exactly one object beats it, a pulsar in the globular cluster Terzan 5, spinning at 716. When this one was announced, it broke a record that had stood for 35 years, held by the very first millisecond pulsar ever discovered, which turns 642 times a second. The second record is the one that matters, and it took nearly 4 years to get. Roger Romani at Stanford, with Dinesh Kandel, and with Alexei Filipenko, Thomas Brink, and Wei-Kang Zheng at Berkeley, measured the mass of the pulsar using the Keck telescope on Mauna Kea. 2 imaging campaigns and 6 spectroscopy campaigns between December 2018 and March 2022. The method works because of that day-night temperature difference. Model how the companion is heated and deformed. Watch how its brightness and its velocity change around the orbit, and the mass of the thing doing the heating falls out. 2.35 solar masses, plus or minus 0.17. The largest well-measured mass of any neutron star on record, against a previous best of 2.08. A follow-up, published in December 2025, tightened it to 2.347, plus or minus 0.107. If this pulsar was born at the standard 1.4 solar masses, as most are, it has since eaten about 0.95 solar masses off its companion. Very nearly an entire sun, transferred one meal at a time across hundreds of millions of years. The name comes from the prototype, found in 1988, a millisecond pulsar in a 9-hour orbit whose companion was visibly being destroyed by the pulsar's particle wind. Astronomers called it a black widow. The naming scheme has grown since. Systems with heavier companions, between 15 and 40 hundredths of a solar mass, are called redbacks after the Australian spider. The whole family is known as spiders. Romani coined a name of his own for the most extreme cases, after a species whose male is 1% the size of the female. A catalogue published in 2025 lists 111 of these systems in the galactic field. Filipenko and Romani have examined about a dozen of them closely. Only 6 had companions bright enough to weigh at all, and every one of those was lighter than this pulsar. For the density, Romani offers the comparison directly. 1 cubic inch of this material weighs over 10 billion tons. That makes this object, by his description, the densest thing within sight of Earth. Filipenko puts the physics differently. A neutron star, he says, is like one giant atomic nucleus. But when you have 1.5 solar masses of the stuff, about 500,000 Earth masses of nuclei all clinging together, it is not at all clear how it behaves. Which is the actual mystery, and it is worth building carefully. There is a maximum mass a non-rotating neutron star can hold before it collapses into a black hole. It is named after Richard Tolman, Robert Oppenheimer, and George Volkoff, who did the original calculation in 1939, treating the interior as a gas of degenerate neutrons. Their answer was a limit of about 0.7 solar masses, which is lower than the limit for white dwarfs, and which we now know is far too low, because their calculation left out the strong nuclear force. Modern estimates put the real limit somewhere between 2.2 and 2.9 solar masses, and the spread in that range is not a measurement error. It is a disagreement about what neutron star interiors are made of. The competing possibilities are exotic. Ordinary nucleons. Hyperons, which are heavier cousins of the neutron containing strange quarks. Condensates of kaons. Or free quarks, dissolved out of their nucleons entirely, filling the core as a fluid. Each of those possibilities makes the interior easier to squash, which lowers the maximum mass a neutron star can support. So a heavy neutron star is an experimental result. Every solar mass you add rules out another set of theories. Ramani's reading of 2.35 is that the interior is likely a mixture of nuclei and their dissolved up and down quarks, all the way to the core, and that many of the more exotic proposals are excluded by this one object. And here is where it gets uncomfortable, because there is a direct conflict in the literature, and it is rarely stated plainly. In 2017, gravitational wave detectors caught 2 neutron stars merging. That event was used to derive an upper limit on the maximum neutron star mass, and the answer came out at roughly 2.17 solar masses. Independent groups working from the same event got comparable ceilings. A neutron star of 2.35 solar masses sits above that ceiling. Either the merger-based upper limits are wrong, or this mass measurement is biased high. Both cannot be correct as written. And the sharpest critique of the mass measurement is in Ramani's own follow-up paper. He raises, unprompted, the example of another pulsar whose mass was measured optically at 2.01 solar masses and later revised downward by about 5 standard deviations when it was measured by radio alone. Those earlier optical values, he writes, were statistically precise and evidently biased. Then, of his own object, our measurement might be subject to similar issues. The precedent is worse than that. In 2023, a team led by Colin Clark used a completely different technique on 49 of these systems. Instead of modeling the companion's light, they used the eclipses of the pulsar's gamma rays, which is a geometric method and largely model-independent. Applied to the original Black Widow, the prototype from 1988, whose mass had been reported at 2.40 solar masses, the geometric method returned 1.81. That team's stated concern is that inclinations derived optically may be systematically biased by heating models that are incomplete. Ramani's defense is specific rather than defensive. This system, he argues, is the cleanest one available. The heating is not extreme. The companion's surface is dominated by hydrogen. It underfills its Roche lobe, so it is not badly distorted. The orbit is long, and unusually for a Black Widow, this system shows no radio eclipses at all, which means there is no thick cloud of ablated material confusing the geometry. A simple direct heating model gives the best fit, and adding hotspots or surface winds does not improve it. That is precisely why this object, rather than a more violent one, carries the record. It It is the one that can be modeled without inventing anything. He concedes his weakest link, honestly, the radial velocities, which require inspecting the data by eye to isolate the signal, and therefore carry some subjectivity. There is one correction worth carrying out of this entry, because it has been repeated everywhere. Nearly every article written about this system says the companion is 20 times the mass of Jupiter. That figure is the minimum permitted by the orbital dynamics, published in 2017, before anyone had weighed anything. The measured value is 33. The lower bound outlived the measurement in the popular record, which is a small illustration of how these numbers travel. A second correction, of a different kind. It is often said that this pulsar will eventually destroy its companion completely. That is a hypothesis, not a measurement. No published source gives an evaporation timescale for this system. Whether the companion is annihilated or stabilizes as a stripped remnant or simply outlives the pulsar's ability to feed on it is not known. Filipenko's own framing of the situation is characteristically dry. In a case of cosmic ingratitude, he says, the Black Widow pulsar, having devoured a large part of its mate, now heats and evaporates the companion down to planetary masses and perhaps complete annihilation. The word perhaps is doing real work in that sentence. Something else has been ruled out, quietly, and it is worth knowing. A neutron star spinning this fast, if it carried any deformation at all in its crust, would radiate gravitational waves continuously, forever, at a frequency set by its spin. That is a searchable signal, and the search was run on this object using the first 2 LIGO observing runs. It found nothing, setting an upper limit on the strain of 6.6 times 10 to the minus 26. Which means this object is, to the precision available, almost perfectly smooth. A 12-kilometer sphere turning 700 times a second, with no measurable bump on it. 2 more details and then we move on. The 2025 analysis applied a rotational support correction. Because the star is spinning at 707 Hz, some of its weight is being carried by rotation rather than by pressure. Corrected to a non-rotating equivalent, the mass drops by 0.026 solar masses. The spin is measurably helping hold the star up, and the correction is small enough to be a footnote and large enough to be worth making. And there is a puzzle nobody has solved about the spin itself. The equation of state permits neutron stars to rotate at something like 1200 Hz before they break apart. The observed population cuts off sharply near 730. There are candidate explanations, including the way accretion ends, gravitational wave breaking, and plane selection bias, and none of them has been established. So, an object 20,000 light-years away, 12 kilometers across, spinning at 18% of the speed of light at its equator, slowly consuming a companion it has already reduced to the mass of a large planet, and the number attached to it decides which theories of matter survive. There is no laboratory on Earth that can make this state of matter, and there is no serious prospect of one. The experiment has already run. We are reading the result off a light curve from a companion star using a model, and the person who made the measurement is the one telling us to be careful with it. The next entry is not an argument about a number. It is an argument about what a star looks like, and it was settled, or unsettled, by the first close-up photograph ever taken of a star outside our own galaxy. Number 6, the Behemoth, in another galaxy. Every star we have looked at so far belongs to the Milky Way. Number 6 does not. It is catalogued as WOHG 64, which is the 64th entry in a catalogue compiled by Bengt Westerlund, Nils Olander, and B. Heading: It sits in the Large Magellanic Cloud, in the direction of the southern constellation Dorado, and its distance is not measured. It is assumed. Membership of the Large Magellanic Cloud puts it at roughly 50 kiloparsecs, about 160,000 light-years. The honest caveat is worth stating, because it is a strange one. The Gaia spacecraft's measured parallax for this star is negative, minus 0.2477 milliarcseconds. A negative parallax is not a small distance or a large one. It is physically meaningless, an artifact of noise on a measurement that is far too small to make. There is no direct distance to this object at all. We locate it by which galaxy it is standing in. At 160,000 light-years, a Voyager speed crossing takes about 2.8 billion years. That is more than half the age of the Earth. The reason to care about this particular star is size, and the size needs contextualizing properly, rather than just quoted. The most widely used figure gives it a radius of 1,540 times the radius of the Sun. Put that in terms of light, which is the only currency that means anything at these scales. Light takes 14.5 seconds to travel around the circumference of the Sun. Around this star, it takes more than 6 hours. If you placed it where the Sun is, its surface would sit beyond the orbit of Jupiter. Mercury, Venus, Earth, Mars, the entire asteroid belt and Jupiter itself would all be inside it. And that is the conservative estimate. Which brings us to the mystery, because at this entry, the unresolved question is not about a number or an event. It is about the shape of the thing, and increasingly, about what kind of object it is at all. The size estimates have moved by a factor of 2, and the reason they moved is dust. This star is buried. There are more than 6 magnitudes of visual extinction between us and its surface, which means less than 1% of its visible light reaches us. Everything we know about it, we know through a shroud that it made itself. It is shedding mass at between 3 and 7 ten-thousandths of a solar mass per year, which is among the highest rates known for any star anywhere. The envelope it has already thrown off is about 1 light-year across and contains between 3 and 9 solar masses of material. It has discarded more mass than most stars ever possess. So when you try to work out how bright the star truly is, you have to model the dust, and what you assume about the shape of the dust decides the answer. Under the old models, which assumed a spherical shell, the star came out at between 490,000 and 600,000 times the Sun's luminosity, with a radius between 2,575 and 3,000 solar radii, implying it was born with more than 40 solar masses. Under a torus model, a donut rather than a shell, it drops to 280,000 solar luminosities and about 1,730 solar radii, implying a birth mass of 25. That difference is not academic. Before the torus model, this star's position on the temperature-luminosity diagram was, in the words of the astronomer who fixed it, in serious disagreement with stellar evolution theory. It was too luminous and too cool to exist. The torus model halved its luminosity and brought it back inside the boundaries. Which is a slightly unsettling thing to notice. The model that saved the theory is the model that was adopted. Its history in the literature is a slow reclassification. Westerlund, Hollander and Hedin catalogued it in 1981 as an unremarkable cool giant. In 1986, Elias, Frogel and Schwering showed with infrared photometry that it was in fact hugely luminous and wrapped in dust, absorbing about 3/4 of its output. Through the 1990s, it was found to be a prominent maser source, emitting in hydroxyl water and silicon monoxide, and pulsating with a period of more than 900 days like an oversized mirror variable. Then, in 2005 and 2007, Keiichi Onaka's team did something new. They used the MIDI instrument on the Very Large Telescope Interferometer, combining light from just two of the telescopes across a 60-meter baseline, and resolved the object in the mid-infrared. That was the first time an individual star in another galaxy had been resolved by interferometry at all. Across 4 different orientations, 60 degrees apart, it appeared nearly symmetric about its center. They modeled it as a thick silicate torus seen close to Polon. The masers are worth a short detour because they are one of the few ways anyone has ever probed the inside of that shroud. A maser is the microwave equivalent of a laser, molecules in a gas pumped by the star's radiation into an excited state, dumping that energy all at once at a single frequency. It happens naturally in the envelopes of cool, dusty, mass-losing stars, and the emission is narrow enough that its Doppler shift can be measured with great precision. So while the star itself is hidden, the water and hydroxyl molecules floating in the material it has ejected are broadcasting their velocities outward. Radio astronomers have been listening to the wind of this star for decades without ever seeing the star. The naming convention is a small piece of history in itself. The 3 letters at the front of the designation are the initials of the 3 people who compiled the catalogue, which was a common practice at the time and produced some of the more human-sounding entries in astronomy. Westerlund, whose W begins it, also discovered a cluster of red supergiants in our own galaxy that now bears his name, and one of the largest stars in it is known by his initial and a number. An actual image required more telescopes and better light. It required gravity, the 4-telescope beam combiner at Paranal, and it required a very particular kind of night. On the 15th and the 26th of December, 2020, 4 8-meter telescopes, standing hundreds of meters apart on a mountaintop in the Atacama, were all pointed at the same smudge of light in another galaxy. Their light was carried down into tunnels beneath the platform, along delay lines that must hold the path lengths equal to within a fraction of the wavelength being observed, and then combined in a single instrument at wavelengths between 2 and 2.5 microns. What comes out of that process is not a photograph. It is an interference pattern, a set of fringes carrying information about the structure of the source, and it has to be reconstructed into an image by computation. The telescopes never see a picture. Nobody at the observatory looks through anything. When the reconstruction ran, the star that was expected to be round was not round. It was an egg. The result was announced in November 2024 as the first close-up image of a star outside the Milky Way. Before it, roughly 24 stars had ever been imaged in any detail, and every one of them belonged to our own galaxy. 24. Out of everything. And the very first extragalactic portrait came back refusing to match the model. The reconstructed emission has a semi-major axis of about 2 milliarc seconds and a semi-minor axis of about 1.5, corresponding to roughly 13 and 9 stellar radii. That is an elongation of about 1/3. Nobody had predicted it. And the 2005 and 2007 data had shown no detectable asymmetry at all across 4 position angles, which means the elongation either appeared or became visible in the interval between the 2 campaigns. The newer data also show the star contributing far less light at 2.2 microns than the earlier torus model said it should. Onaka's paper offers 2 explanations for the shape and does not choose between them. Either the star is losing mass in a bipolar outflow rather than uniformly, or there is an unseen companion shaping the material. Then the strangeness compounds. the near-infrared spectrum of this star changed fundamentally somewhere between December 2009 and 2016. Before 2003, it showed the recognizable photosphere of a red supergiant, with water absorption bands where they belong. After 2016, it shows a continuum rising smoothly with wavelength and the water almost entirely gone. But a mid-infrared spectrum taken in 2022 matches the pre-2007 spectra closely. Whatever changed close to the star. The outer envelope, the light-year-wide cocoon, did not notice. Its pulsation shortened, from more than 900 days in the 1980s to less than 900 by around the year 2000, and around 2014, the variation stopped being semi-regular and became irregular. Its spectral type warmed, from M7.5 in the 1990s to M5 a decade later. One survey has classified it not as a supergiant at all, but as a carbon-rich, long-period variable, which would make it a much less massive star on the asymptotic giant branch, a completely different kind of object with a completely different future. And it is fading. It was measured at 15.34 in the red in February 2018, and at around 17.8 by November 2024. About 2 magnitudes, a factor of 6 in 6 years. Which means that imaging this star is getting harder with time, not easier. The window in which the first extragalactic close-up was possible may already be closing, all of which has produced an argument that is running right now between people who have both been working on this star for years. One team argues that WOHG 64 has undergone the most extreme transition ever seen in the optical spectral features of a red supergiant. In their reading, it is no longer a red supergiant. It has become a yellow hypergiant, roughly half its former size at around 800 solar radii and 4,700 Kelvin, sitting inside a rare and massive symbiotic binary with a B-type companion. The mechanism is either partial ejection of its outer atmosphere during a common envelope phase or a return to quiescence after an eruption lasting 30 years. Jaco van Loon and Keiichi Onaka disagree, and they published a paper saying so with a title about a phoenix rising from the ashes. They present 9 spectra, taken between November 2024 and December 2025 with the Southern African Large Telescope. In every one of those 9 spectra, titanium oxide absorption is present. Titanium oxide is a molecule that only survives in a cool atmosphere. It is the molecular fingerprint of a red photosphere. Their conclusion is that the star is currently a red supergiant and may never have stopped being one. Their proposed mechanism is a close passage of a companion star, tightening the Roche lobe, stretching the atmosphere, and exposing a deeper and warmer layer temporarily. For that to work, the orbital period has to be longer than a century. So 2 teams, both experienced, both looking at overlapping data on the same object, currently disagree about what color it is. Which is another way of saying they disagree about what kind of star it is, how massive it is, and how it is going to die. It is worth being clear about what is actually at stake in that disagreement, because it sounds like a labeling argument, and it is not. A red supergiant is a massive star in its final act. It has burned through the hydrogen in its core, swollen enormously, and is now working through progressively heavier fuels while shedding its outer layers. Its ending is a core collapse supernova, and the timescale from here is short in stellar terms, perhaps 100,000 years. A yellow hypergiant is something else. It is a star that has already lost most of its envelope and is moving back across the temperature diagram toward the blue, hotter and smaller than it was, in a phase that is both rare and brief. Only a handful are known anywhere. If this star has genuinely made that transition, then we have watched a stage of massive stellar evolution happen in real time over about 15 years. That theory says takes far longer and that nobody has ever directly observed. And if it is a carbon-rich star on the asymptotic giant branch, as one survey classification would have it, then it is not a massive star at all, will never produce a supernova, and every mass estimate ever published for it is wrong by a large factor. 3 possible identities, 3 different deaths, 1 object, and the data currently supports arguments for more than one of them. Disks of this kind are not unique to it. Comparable structures have been found around 2 much closer stars in our own galaxy, one in Canis Major and one in Cepheus, both of them enormous red supergiants shedding material at a great rate. What is unique here is location. Those stars are a few thousand light-years away and have been studied by every instrument built in the last 50 years. This one is 160,000 light-years away, in a different galaxy, and it took a virtual telescope 130 meters across, working at the limit of what interferometry can do, just to establish that it is not round. A few things worth carrying out of this entry. The most cited modern paper on the star is titled with a question mark. It asks whether this is the largest star known, and then does not answer. That same paper, in 2009, proposed a hot companion star 15 years before anyone argued for one seriously. The evidence was a velocity shift of 50 kilometers per second between the nebular emission lines coming from the surrounding gas and the star's own spectral features. Something else was in there, moving. The very large telescope interferometer, which made all of this possible, is a virtual instrument. Its resolving power is set by the distance between the telescopes, not by the size of their mirrors. 4 8-meter mirrors, separated by 130 meters, resolve like 130 meters telescope, and nothing like one collects light. Which is why the star being faint matters so much, and why the stated path forward is an upgraded version of the same instrument. And this star sits near 2 theoretical boundaries at once. The Hayashi limit describes the coolest a star of its type can be and remain in equilibrium. The Humphreys-Davidson limit describes the most luminous a cool supergiant can be before it becomes unstable. It is pressed against both. Its current mass is estimated at about 20 solar masses, down from 25 or more at birth. It has already thrown away a fifth of itself, and it is not finished. The first close-up any human being has ever seen of a star belonging to another galaxy came back the wrong shape, from an object whose classification is under active dispute, which is fading fast enough that the picture may not be repeatable, at a distance where the only thing that will ever reach us from it is light. The next entry on this list is not a disagreement about a star. It is a disagreement about whether a star died at all, and it concerns the brightest thing human beings have ever recorded. Number 5. The brightest thing ever recorded. Every object so far has been within about 200,000 light-years. Number 5 is 3.82 billion light-years away. That is a jump worth pausing on, because the numbers stop behaving. At Voyager speed, the crossing takes roughly 67 trillion years. The universe is 13.8 billion years old. The trip is about 5,000 times longer than everything that has ever happened. So let us be generous. Let us imagine a propulsion system nobody has built and nobody knows how to build, running at 1% of the speed of light. That is 3,000 kilometers per second, 176 times faster than Voyager, and it is roughly the upper bound that serious interstellar flight studies are willing to talk about. At 1% of light speed, a light year takes 100 years. 382 billion years. The object is catalogued as ASASSN-15LH, and it also carries a supernova designation SN 2015L. It sits in Indus, a faint southern constellation. Its redshift is 0.2326, measured from magnesium absorption lines. And in the middle of 2015, it became the brightest thing human beings have ever recorded. The light that carried that news left its source 3.82 billion years ago. The Earth existed then, and had existed for something like 800 million years. There were no plants, no animals, no fungi, nothing with more than one cell. Whatever was alive was microscopic and confined to water. That light then traveled for the entire subsequent history of life on this planet. The oxygenation of the atmosphere, the first multicellular organisms, the Cambrian, the forests, the dinosaurs, the mammals, the whole of human history, down to the last person who looked up at the sky and wondered about it, all of that happened while this light was in transit. And at the end of the journey it landed on a camera lens 14 centimeters across. That detail is not incidental. The All-Sky Automated Survey for Supernovae is run out of Ohio State University, and it works by placing small robotic units at sites around the world, each carrying a handful of lenses about the size of a large telephoto. Not research telescopes. Lenses. The unit that caught this one is stationed at Cerro Tololo in Chile and is nicknamed Cassius. The strategy is not depth. It is coverage. Photograph the entire sky every night or two, compare against yesterday, and flag anything new. The detection came on the 14th of June, 2015. Going back through the archive, the object had already been recorded, unnoticed, on the 8th of May at magnitude 17.4. It peaked at 16.9 on the 5th of June and had faded to 18.2 by September. It was formally christened as a supernova on the 24th of July. The confirming spectrum came from the 2.5-meter DuPont telescope at Las Campanas. The redshift came from the Southern African Large Telescope, and the redshift is what turns a bright dot into a number, because the redshift gives the distance, and the distance turns apparent brightness into actual output. The Swift satellite, built to chase gamma-ray bursts, supplied ultraviolet and X-ray follow-up. The lead author was Subo Dong at the Kavli Institute for Astronomy and Astrophysics at Peking University, and the paper appeared in January 2016. 4 continents and a 14-centimeter lens at the front of it. Here is what the redshift converted the dot into. Peak absolute magnitude in the ultraviolet of -23.5. Peak output of 2.2 times 10 to the 45th ergs per second. In plain terms, roughly 570 billion times the luminosity of the Sun, and about 20 times the combined light of the entire Milky Way galaxy. Every star in our galaxy, added together and then multiplied by 20. From one point, in its first 4 months alone, it radiated 1.1 times 10 to the 52nd ergs. More than twice as much energy as any previously known supernova, and roughly double the previous record holder in its own category. Krzysztof Stanek, one of the survey's principal investigators, gave the comparison people actually remember. If it had gone off in our own galaxy, it would shine brighter than the full moon. There would be no night, and it would be easily visible during the day. The photospheric radius at maximum exceeded 70,000 solar radii. That is not a surface in any ordinary sense. It is an expanding fireball, far larger than any star could be, whose edge is simply the place where the material becomes transparent. and the spectrum was almost featureless. No hydrogen, no helium. Just two very broad absorption troughs and an enormous hot continuum, starting near 20,000 Kelvin and settling to about 11,000 by 50 days, then staying roughly flat. One more record needs qualifying, because superlatives in astronomy are usually narrower than they sound. This object holds the record for peak luminosity. It does not hold the record for total energy emitted. Another transient, catalogued a few years earlier, put out more energy overall while never reaching the same instantaneous brightness. Brightest is not the same as largest. A thing that burns very hard for 4 months and a thing that burns steadily for years can both be at the top of a list, and they will not be the same list. It is also worth knowing what class this was assigned to, because the class itself is young. Superluminous supernovae were only recognized as a distinct population in the late 2000s, when automated surveys started finding explosions 10 to 100 times brighter than ordinary ones. They come in two broad kinds. Some are rich in hydrogen and are powered, at least in part, by the shock plowing into dense material the star shed before it died. The others show no hydrogen at all, and what powers them has never been settled. The category this object was placed in is the second one, which means it was assigned, on the day of its announcement, to the group of explosions we understand least, and then immediately became the most extreme member of it. Which brings us to why this is on a list of mysteries rather than a list of records. The first problem is the address. Hydrogen-poor superluminous supernovae are found almost exclusively in small, blue, actively star-forming dwarf galaxies. That is not a preference, it is a consequence. Those explosions come from extremely massive stars, and extremely massive stars live for only a few million years, so they only exist where stars are currently being made. This one went off in a large, red, passive galaxy. Bigger and more luminous than the Milky Way, with very little star formation happening anywhere in it. And when the astrometry was improved, the position moved onto the galaxy's nucleus. The second problem is that the light curve had two humps. About 90 days after the primary peak, the Swift satellite recorded the object getting brighter again in the ultraviolet. 1.75 magnitudes in the far ultraviolet band, 1.25 in the middle band, 0.8 in the near band. And there was no corresponding rebrightening in visible light at all. That was followed by a plateau of about 120 days, and then renewed, fading around day 210. The third problem is the most diagnostic, and it needs explaining because it is not obvious. When a supernova expands, its ejecta thin out, and at some point they become transparent enough that we stop seeing a hot surface and start seeing straight through to the glowing gas within. At that stage, the spectrum changes character completely, filling with narrow, forbidden emission lines from atoms so widely spaced they almost never collide. It is called the nebula phase, and every supernova gets there eventually. It is how supernovae end. This one went through 3 distinct spectroscopic phases in 10 months, and never became nebula. It also never showed the narrow emission lines that would indicate it was plowing into surrounding material. So the two camps. The first camp holds that this was a supernova, the most luminous ever seen. The absence of both hydrogen and helium points to a heavily stripped massive star, a Wolf-Rayet, with perhaps 40 solar masses of ejecta. But Dong's own abstract concedes the difficulty. The radiated energy challenges the magnetar model for its engine. That model is worth a sentence, because it is the standard explanation for these events. When a massive star collapses, it can leave behind a newborn neutron star spinning extremely fast with an extremely strong magnetic field. As that field breaks the spin, the rotational energy is dumped into the surrounding debris, and the debris glows. To make an object this bright, one analysis requires an initial spin period of 1 to 2 milliseconds, with a field around 10 to the 14th Gauss. Another gets 0.7 milliseconds. But there is a hard ceiling on how much rotational energy a neutron star can hold before it either flies apart or radiates the excess away as gravitational waves, and a 1 millisecond birth spin runs straight into it. The alternative engine, radioactive nickel, was tested in a paper whose title simply asks how much radioactive nickel this thing requires. The answer is more than a supernova can plausibly make. The second camp holds that this was not a star dying. It was a star being eaten. A large international team led by Georgos Leloudas argued from 10 months of continuous monitoring that this was a tidal disruption event, a star torn apart by the supermassive black hole at the center of that galaxy. Their evidence is the ultraviolet rebrightening, the 3 spectroscopic phases that never went nebula, a temperature evolution that matches disruptions rather than explosions, highly ionized gas along the line of sight, and the improved position placing it in the nucleus of a galaxy where massive stars are highly unlikely to exist. The physics of that argument is elegant, and it is the part worth carrying away. A tidal disruption happens when a star passes close enough to a black hole that the difference in gravitational pull across the star exceeds the star's own self-gravity, and the star is pulled apart. Roughly half the debris is flung away, and the other half falls back and forms a hot disk, and the disk is what we see. But the distance at which a star is torn apart is fixed by the star. The size of the event horizon grows with the black hole's mass. For a sun-like star and a non-rotating black hole above about 100 million solar masses, the tearing point lies inside the horizon. The star is swallowed whole, intact, and nothing at all is emitted. No flare. Silence. The black hole in this galaxy is above 100 million solar masses from the standard scaling relations. Later work put it nearer 500 million, and one analysis argued for a maximally rotating billion. So if this was a disruption, the black hole must be spinning rapidly. A spinning black hole drags space-time around with it, which pulls the innermost stable orbit and the effective tearing radius back outside the horizon, allowing debris to escape and shine. The rapid spin is not an add-on to the explanation. It is required by it. And a rapidly spinning, very massive black hole would also naturally explain the extreme brightness. Follow-up work supports the address. Hubble imaging combined with spatially resolved spectroscopy found the dominant stellar population at the exact position to be old, 1 to 2 billion years, with no sign of recent star formation and emission line ratios indicating a weak active nucleus. Persistent soft X-ray emission has been detected from the site at 10 to the 41st to 42nd ergs per second, which is modest for an active galaxy, but is exactly the residue an accreting supermassive black hole leaves behind. Radio observations at high sensitivity exclude a relativistic jet. Against the disruption reading, there is one serious objection. Real tidal disruptions shred stars made of hydrogen and helium, and this spectrum showed neither in emission. That is not a small problem. There is a rarity argument underneath all of this that is easy to miss. Tidal disruptions are not common. A given galaxy is expected to shred a star perhaps once every 10,000 to 100,000 years, which means that across the whole observable sky, only a few dozen have ever been caught. Superluminous supernovae are rarer still as a fraction of all explosions, occurring perhaps once for every few thousand ordinary supernovae. So, whichever interpretation is correct, this object is an outlier inside an outlier. The disagreement is not between a common explanation and an exotic one. It is between two rare things, both of which would be at the extreme end of their own populations. The host galaxy deserves one more line, because it is doing a great deal of the argumentative work. Its absolute infrared magnitude is around -25.5, which makes it considerably brighter and therefore considerably more massive than the Milky Way. And it is red. Redness in a galaxy is not a color so much as a biography. It means the blue, short-lived, massive stars have all died and nothing has replaced them. The galaxy has finished making stars. It is a place where an explosion requiring a 40 solar mass progenitor is very hard to arrange, and a place where a large, well-fed central black hole is entirely expected. That is the crux, stated plainly. To keep the supernova interpretation, you need a very massive young star in a galaxy that has not made one in a billion years. To keep the disruption interpretation, you need a black hole spinning near its theoretical maximum, and you need to explain a spectrum with no hydrogen and no helium emission in it. Neither camp has a comfortable position. Both camps are staffed by people who know the other side's objection perfectly well. Gravitational lensing, the obvious way to fake extreme brightness, was considered and excluded. There is no suitable foreground cluster, and the geometry is wrong. Several more exotic ideas were published and have not gathered support, including a quark nova inside a Wolf-Rayet remnant and a newborn strange quark star. A decade on, both main interpretations remain in circulation. The brightest event ever recorded by human beings has no agreed cause. The discovery paper is, in effect, a statement of not knowing, and the follow-up literature has not resolved it. There is a small irony in the naming, too. The object received a formal supernova designation on the 24th of July, 2015, 6 weeks after it was found and months before anybody argued about what it was. Under the conventions of astronomical naming, that designation is permanent. So if the disruption interpretation eventually wins, the catalogues will continue to carry an entry labeled as a supernova for something that was never a supernova at all. The record will preserve the first guess. That is not carelessness. It is simply what happens when the naming has to come before the understanding, which in this field it almost always does. We are halfway down. It is worth stopping for a moment to look at what has already gone past. An ordinary subgiant 200 light-years away, measured by 4 generations of astronomers, whose age still cannot be pinned down within 2 billion years. A star observed for a century by careful people who could not name it, because nobody thought to check whether it was magnetic. A red giant near the center of the galaxy that had 97% of its light removed for most of a year by something large, dark and elongated that has never been identified. A 12-kilometer object spinning 700 times a second whose weight decides which theories of matter survive, measured by a man who then published the strongest argument against his own method. A star in another galaxy whose first close-up portrait came out egg-shaped and whose classification 2 teams are currently disputing. And a light so bright it would have abolished night, whose own discoverers cannot say whether it was a death or a meal. Notice what all 6 have in common. Every one of them is a question about how a star behaved. Something moved, or dimmed, or spun, or exploded, and we cannot fully account for the behavior. Everything below this point is different. From here down, every remaining entry is a question about how a star came to exist at all. And the first of them is a star that, by every model we have, should never have been able to form. Number 4, the star with no iron. Number 4 brings us back inside our own galaxy, and much closer. It is about 6,000 light-years away, in the small southern constellation Hydrus, and its catalogue designation is SMSSJ 0313-6708. 6,000 light-years is a Voyager crossing of about 106 million years, which by the standards of the last entry counts as a neighbour. Its apparent magnitude is 14.7, which means any research telescope in the world can observe it comfortably, and no amateur instrument will show it. It is a K-class red giant. Photographed, it looks like nothing. There are hundreds of thousands of stars in the southern sky that look exactly like it. It is approximately 13.6 billion years old, which means it formed roughly 200 million years after the Big Bang. And it contains no detectable iron. That phrase needs handling precisely, because it is easy to overclaim, and the overclaim would be a disservice to what is actually a stranger result. It does not mean the star contains no iron. It means that no spectrograph anyone has pointed at it has been able to find any. There are no iron lines in its spectrum. Not weak lines. No lines. What astronomers publish in that situation is not a measurement but an upper limit. Iron must be below a certain amount, or we would have seen it. The Discovery paper put that limit at -7.30 on the standard logarithmic scale where the Sun is 0, and applying a three-dimensional correction for the physics of its atmosphere gave the headline figure of -7.1. That is less than 1/10,000,000th of the Sun's iron content, and at least 30 times lower than any star previously known. Then, in 2017, a full three-dimensional reanalysis revised the limit upward by a factor of 10 to -6.53. The difference came from a more conservative treatment of how upper limits are estimated, updated atomic data, and genuine differences between the three-dimensional model and the averaged one. Both numbers are in the literature. The stricter one is the discovery value, and it is not undisputed. There is something worth noticing here that connects back to where this list began. At number 10, the age of the Methuselah star kept moving because the instruments kept improving, and the record was really a statement about our instruments. Here the same thing is true, and it is inverted. This record cannot be improved by better equipment in the usual direction. A better spectrograph would not raise the record. It would lower it because it would push the limit further down, or it would find the lines and end the record entirely. The number is not describing the star. It is describing the boundary of our ability to see. What the star does contain is carbon, in quantity. Relative to iron, and compared with the Sun, carbon is enhanced by more than a factor of 1,000. Magnesium is there. Calcium is there. The molecule methylidyne, carbon bonded to hydrogen, is detected by its absorption band. And no oxygen and no nitrogen have been detected at all, which is itself difficult to fit. The discovery came from a telescope built to look at everything rather than at anything. The SkyMapper Southern Sky Survey uses a fully robotic 1.35-meter telescope at Siding Spring Observatory near Coonabarabran in New South Wales, Australia. Its purpose is to photograph the entire southern sky repeatedly in 6 filters. One of those filters is the key to this whole result, a narrowband filter positioned over the calcium K line. The calcium K line is one of the strongest absorption features in the spectrum of a cool star, and its strength scales with how much metal the star contains. Measure how much light a star is missing in that narrow band, compared with the bands on either side, and you have a rough metal content from photometry alone, without ever taking a spectrum. That is what makes the search possible. Spectroscopy on a 6-meter telescope is expensive and slow. Photometry on a 1-meter telescope is cheap and covers the sky. The survey screens millions of stars photometrically so that a handful can be put on the big instrument. The work was led by Stephen Keller at the Australian National University. Confirmation came first from a low-resolution spectrum on the ANU 2.3-meter telescope, and then from high-resolution spectroscopy on 5 separate nights in January and February 2013, using the Mike spectrograph on the 6.5-meter Magellan Clay telescope at Las Campanas in Chile. The paper appeared in Nature in February 2014. Among its co-authors was Brian Schmidt, who had shared the Nobel Prize in Physics 3 years earlier for the discovery that the expansion of the universe is accelerating. Now, why a star with no iron is a star that should not exist? The universe began with hydrogen, helium, and a trace of lithium. That is all. Every other element, including every atom of iron in your blood, was manufactured inside a star and released when that star died. So the very first generation of stars, the ones astronomers call population 3, formed from gas with no metals in it at all. Nothing else was available. Nobody has ever found one. The second generation formed from gas that had been enriched by the deaths of the first. And the less enriched a star is, the earlier it must have formed, and the fewer prior stellar deaths contributed to it. Which makes this object the closest thing anyone has to a chemical fossil of that first generation. The pattern of what is present and what is absent is the whole result. Carbon, magnesium, and calcium, but no iron. Iron is made in the deepest, hottest layers of a massive star, right at the center, immediately around the core that will collapse. Carbon and magnesium are made further out. So an explosion that scatters the outer layers but fails to eject the innermost ones would enrich the surrounding gas with light elements and almost no iron. That is exactly the interpretation. The team argues that the gas that made this star was enriched by a single population 3 star of roughly 60 solar masses, which died as a low-energy supernova in which the iron-bearing core material fell back onto the compact remnant instead of escaping. The iron was made. It simply never got out. Read that claim carefully, because it is remarkable. The abundance ratios indicate enrichment by at most a few, and potentially only one, prior explosion. This is a star built from the ashes of what may have been a single individual first-generation star, whose identity, mass, and manner of death are readable 300 million years later in the light of the star it fathered. It also overturns something that had been the favored picture for years, and this is the part with the widest consequences. Theory had long expected the very first stars to end in an exotic and enormously violent way. A star above roughly 140 solar masses can reach a core temperature at which photons begin converting spontaneously into electron-positron pairs. That conversion removes radiation pressure from the core loses its support, it contracts, the contraction ignites the remaining oxygen explosively, and the entire star is destroyed. Nothing is left behind, no neutron star, no black hole, and the explosion scatters everything it made, including a great deal of iron, across a large volume. That is called a pair instability supernova, and if the first stars died that way, the second generation should carry its fingerprint, a distinctive pattern of elements, and plenty of iron. We do not see that fingerprint. Not in this star, and not clearly in any of the extremely metal-poor stars found so far. What we see instead points the other way, toward explosions that were relatively feeble, that failed to eject their own centers, and that seeded the next generation with light elements while keeping the heavy ones. Keller's own framing of the implication is direct. The first supernovae may have been far less energetic than previously assumed. That is a substantial revision, and it is being made on the basis of what a handful of faint stars in the southern sky do not contain. A follow-up analysis in 2015 went after the carbon and oxygen specifically, because those two elements together are the most sensitive probe of the explosion that made them. The ratio between them constrains how deeply the progenitor was mixed before it blew, and how much of its interior fell back. A single star, in other words, is being used as a forensic reconstruction of an explosion that happened 13.5 billion years ago and left no other trace anywhere. What is unresolved? The progenitor mass is contested. The discovery team argues for about 60 solar masses, and a competing group argues for faint first-generation supernovae of around 25 solar masses undergoing mixing and fallback, which they say reproduces the entire class of most iron-poor stars, rather than this one alone. A third group proposes a different mechanism altogether, an intermediate neutron capture process operating in the first stars. And the iron limit itself, as we have seen, has already moved by a factor of 10. For calibration, it helps to know the company this star keeps. Two stars found by an earlier German survey sit at about -5.3 and -5.4, both strongly enriched in carbon, nitrogen and oxygen, and the second of those held the record before this one. Then there is the awkward one, found in Sloan data and usually named after the astronomer who analyzed it, at -4.89. It is awkward because it is not carbon-enhanced. It shows no measurable enhancement of carbon or nitrogen at all, which places it in what theorists had called the forbidden zone, the region where star formation was supposed to be impossible, because without carbon and oxygen, the gas cannot cool efficiently enough to fragment into small stars. Its existence undermines the idea that peculiar chemistry is required at low metal content, and nobody has satisfactorily explained it. The cooling argument behind that forbidden zone is worth understanding, because it is the same physics that governs the whole question of the first stars. A cloud of gas collapsing under its own gravity heats up as it contracts, and heat means pressure, and pressure resists collapse. For the collapse to continue, the cloud has to get rid of that heat, and the only way to do that is to radiate it away. Radiating requires something in the gas that can absorb a collision and re-emit the energy as light that escapes. Carbon and oxygen are extremely good at this. Hydrogen and helium are poor at it. So a cloud with a little carbon and oxygen in it can shed heat, keep collapsing, break into small fragments, and make small stars. A cloud with neither stays warm, resists fragmentation, and makes a few enormous ones. Which is why finding a star that is both metal-poor and carbon-poor was a genuine problem. It should not have been able to cool enough to form at the mass it did. And in 2019, another SkyMapper star took a different record, the lowest iron abundance ever actually detected, at -6.2. Its iron content is about 1 part in 50 billion. The team's own comparison was 1 drop of water in an Olympic swimming pool. Roughly 1.5 million times less iron than the Sun. The distinction between those two records is worth stating plainly, because they get confused constantly. One star holds the record for the lowest detected iron abundance. Tonight's entry holds the record for the lowest upper limit. In one case, the iron was found and measured. In the other, it was looked for and not found. They are different achievements, and only one of them is a measurement. Which brings us to the deeper absence, the one the whole field circles around. No true population 3 star has ever been found. Not in the Sloan Digital Sky Survey, not in the Hamburg Survey, not in SkyMapper, not anywhere, despite decades of dedicated searching by multiple independent groups on multiple continents. That absence is itself the strongest piece of evidence we have about the first stars, and the logic runs like this. How long a star lives depends almost entirely on its mass. Massive stars burn through their fuel in a few million years. Small stars burn slowly. Anything below about 8/10 of a solar mass has a main sequence lifetime longer than the current age of the universe, which means that if any such star ever formed at any point in cosmic history, it is still shining right now. So if the first generation had included large numbers of small stars, some of them would still be here, and we would have found them. We have not found one, which suggests the first generation was overwhelmingly massive and short-lived, and there is a physical reason to expect that. Primordial gas contains no metals and no dust, and metals and dust are what allow a collapsing cloud to radiate away its heat efficiently. Gas that cannot cool cannot fragment into small pieces. It collapses in large clumps and makes large stars. There is a nice symmetry in how the two great telescopes of this field divide the work, and it is worth spelling out because it explains why a result like this takes a decade rather than a night. The survey telescope is small, cheap to run, fully automated, and photographs everything. It does not understand anything it sees. Its job is to reduce 100 million stars to a list of a few hundred worth a closer look. The large telescope is expensive, oversubscribed, and can only look at one object at a time, but it can take that object apart, wavelength by wavelength. Neither instrument could produce this result alone. The one that found the star could never have proved anything about it, and the one that proved it would never have found it. And the age figure deserves a note, because 13.6 billion years sounds like a measurement and is not quite one. Nobody has dated this star directly. Its age is inferred from the fact that it must have formed before the gas around it was enriched, and from models of how quickly enrichment proceeded in the early universe. It is a chronology built from chemistry rather than from a clock, which is why the number is quoted as approximate and why it is compatible with, rather than derived from, the age of the universe. The honest caveats are two. A genuine first-generation star could have swept up interstellar material over billions of years and coated its own surface with metals it never made, disguising itself as a merely metal-poor star. And every survey ever conducted is limited by how faint it can see and biased by what it chose to look at. This is not settled. There is even a selection effect built into tonight's record. This object is a red giant, and giants are luminous. That is why the survey could find one at 6,000 light-years. An equivalent star that had not yet swollen would be far fainter and would have been invisible to the same search. The record holder is not necessarily the most extreme star. It is the most extreme star bright enough to be found. So, an ordinary-looking 14th magnitude giant in a small southern constellation, 6,000 light-years away, carrying in its atmosphere what may be the chemical signature of one individual star that died before the Earth, the Sun, or the Milky Way in anything like its current form existed. The message is written entirely in what is missing from it, and reading it correctly changes what we believe about how the first light in the universe was made. That star formed where nothing was preventing it. The next entry on this list is about roughly 100 stars that formed in the one place in the galaxy where the physics says nothing can form at all. Number 3. The stars that should not be there. Number 3 is not one star. It is roughly 100 of them, and they are all in the same place, and that place is the center of our own galaxy. The distance is 26,670 light-years, and it is worth knowing how well that is now known. The gravity collaboration measured it geometrically in 2019 at 8,178 parsecs, with a statistical uncertainty of 13 parsecs and a systematic uncertainty of 22. That is a precision of 3 parts in 1,000 on the distance to the center of the galaxy, which was uncertain by 10% within living memory. The mass of the black hole sitting at that center is 4.30 million solar masses, known to 1/4%. At Voyager speed, the crossing takes about 470 million years. Around that black hole, packed inside a region about 4/100ths of a parsec across, sits a swarm of stars astronomers call the S-cluster. They are mostly B-type main sequence stars, and their orbits are randomly oriented and highly eccentric, like a shell of bees rather than a disk. 12 years of spectroscopy put their masses between 8 and 14 times the Sun's. The best studied of them, S2, has been dated at about 6.6 million years old. Farther out, between roughly 4/100ths and half a parsec, there is something different, a coherently rotating sheet of O-type and Wolf-Rayet stars, known as the clockwise young stellar disk, first identified in 2003 from 13 stars, 10 of which turned out to lie in a single thin plane. All of these stars are young. That is the entire problem, and Andrea Ghez and her colleagues named it in a paper title in 2003, A Paradox of Youth. Here is the physics, and it is straightforward enough to state exactly. For a cloud of gas to collapse into a star, it has to hold itself together against everything trying to pull it apart. Near a black hole of 4 million solar masses, the dominant thing pulling it apart is tidal shear. The near side of the cloud feels a stronger pull than the far side, and the difference stretches and shreds it. To survive that, the cloud has to be denser than a critical value, and that critical value scales as the inverse cube of the distance from the black hole. Move 3 times closer and you need 27 times the density. At 1 parsec from the black hole, the required density is roughly 200 million particles per cubic centimeter. At 1/10 of a parsec, it is more than 10 billion. The molecular gas actually observed in that region sits between 1 million and 10 million particles per cubic centimeter. It is short by 3 to 4 orders of magnitude. Stars cannot form there. There are stars there, and some of them are only a few million years old, which in stellar terms means they were born after our own species had already appeared on Earth. Before the names and the dates, one practical point about why this took so long. The center of the galaxy cannot be seen in visible light at all. There is so much dust between us and it that visible light is dimmed by something like 30 magnitudes, which is a factor of 1,000,000,000. Nothing gets through. Every observation of these stars, every orbit, every velocity, has been made in the infrared, where the dust is far more transparent. And infrared astronomy from the ground is difficult because the sky itself glows in the infrared and the atmosphere blurs everything. The field only became possible when adaptive optics arrived, deformable mirrors that measure the atmosphere's distortion hundreds of times a second and bend themselves to cancel it out. So the map of the galactic center was assembled by 2 competing groups on 2 different mountains over 30 years, each of them photographing the same handful of arc-seconds of sky again and again, watching a few dozen points of light move. The observational story behind all of this is one of the genuine achievements of the last half-century, and it deserves the names and the dates. SES-2 orbits the black hole once every 16 years. Its closest approach happened on the 19th of May, 2018, at a distance of 120 astronomical units, moving at 7,700 kilometers per second. 120 astronomical units is 4 times the orbit of Neptune, so even at its closest, this star is not skimming anything. but 7,700 kilometers per second is about 2.5% of the speed of light, and at that speed, relativity stops being a correction and becomes a measurement. Two teams raced that passage. The gravity collaboration, led from the Max Planck Institute for Extraterrestrial Physics by Reinhard Genzel with Frank Eisenhower and Stefan Gillissen, uses the same 4-telescope interferometer we met at number 6, combining the light of 4 8-meter telescopes. They reported the combined gravitational redshift and transverse Doppler shift later that same year, light climbing out of the black hole's gravity well, stretched by exactly the amount Einstein's theory requires. The Euclid group under Andrea Ghez, working at Keck in Hawaii, published the independent confirmation in July 2019. Their measurement came out at 0.88 times the general relativistic prediction, with an uncertainty of 0.17. Consistent with Einstein, and inconsistent with Newton at 5 standard deviations. The following year, gravity detected something subtler. S2's orbit is not a closed ellipse. Each time it goes round, the entire ellipse rotates slightly in its own plane, by 12.1 arc-minutes per orbit. This is the same effect that shows up in Mercury's orbit around the Sun, where it amounts to 43 arc-seconds per century, and helped confirm general relativity 100 years ago. Here it is thousands of times larger, on a star, around a black hole, measured directly. In 2020, Reinhard Genzel and Andrea Ghez shared half of the Nobel Prize in Physics for the discovery of a supermassive compact object at the center of the galaxy. And the orbits have kept getting tighter since. Florian Peisker and colleagues have reported stars on far shorter periods, including one with a 4-year orbit reaching about 8,000 kilometers per second, and another on an orbit so elongated that its closest approach is around 12.5 astronomical units, and its peak velocity is roughly 24,000 kilometers per second, about 8% of the speed of light. Those identifications are contested. The gravity team has stated publicly that its data are inconsistent with one of them, and suggested that 2 stars were confused with each other in lower resolution imaging. Peisker's group has replied with detections it argues are free of that confusion. That argument is unresolved, and both sides are still publishing. What is not contested is the newest result, and it is days old. In August 2026, the Gravity Plus collaboration published the discovery of a star designated S301. Its orbital period is 8.7 years. Its closest approach to the black hole is just over 12 astronomical units, which is roughly the distance from the Sun to Saturn. At that point, it is moving at about 25,000 kilometers per second, above 8% of the speed of light. It is about 2 billion times fainter than Betelgeuse. It was first detected in the spring of 2023, and once it was found, its orbit was reconstructed backward through archival data to 2017. Its last close passage was in early 2023. The next one falls in 2031. And it is the first star whose orbit is measurably affected by the rotation of the black hole itself. That effect has a name. A spinning mass does not simply curve spacetime, it drags spacetime around with it, like a spoon turning in honey. Orbits inside the dragged region are twisted, their planes slowly rotating. It is called frame dragging, and it has been measured before, around the Earth, using satellites, at the very edge of detectability. Measuring it around Sagittarius A star would give the first direct dynamical measurement of how fast a supermassive black hole spins, which is a number nobody has ever had. The team expects to get it within about a decade. The astronomers involved described the detection as trying to hear the buzz of a fly while an orchestra is playing. Follow that star inward for a moment. It is falling on an orbit that will bring it to 12 astronomical units of a 4 million solar mass black hole, and it is accelerating the whole way. At its fastest, it covers 25,000 kilometers in 1 second. The distance from the Earth to the Moon takes it about 15 seconds. The distance from the Earth to the Sun takes it about an hour and a half. Ahead of it, the sky is crowded. At that speed, the stars in front are shifted toward the blue and squeezed into a smaller patch of sky than they occupy from any resting frame. And the black hole itself is not a hole in the view. It is a dark circle, and around its edge, the light of everything behind it is bent into a ring, so that the sky appears to wrap around the darkness rather than stop at it. The passage takes months, not moments. Then the star climbs back out, decelerating, and heads for the far end of an orbit it has been running for millions of years. Nothing about it is unstable. It is not falling in. It is simply a perfectly ordinary star, in a perfectly stable orbit, somewhere nothing should have been born. So, how did they get there? 3 explanations compete, and none has won. The first is in situ formation. If the black hole was once surrounded by a massive accretion disk, that disk could become dense enough in places to collapse under its own gravity and make stars directly, beating the tidal threshold because the disk supplies the density. That was proposed in 2003 by Yuri Levin and Andrei Beloborodov, and it explains the clockwise disk very well, because a disk that formed from a disk would still be a disk. It does not explain the S cluster, whose orbits point in every direction. The second is migration. A dense star cluster forms further out, where formation is easy, and then spirals inward through dynamical friction, dissolving as it goes and leaving its stars behind. That was proposed by Ortwin Gerhard in 2001, and there is even a candidate surviving core still visible near the center. The objection is that the calculations suggest such a cluster would stall around 25 parsecs out and never make the journey in the time available. The third is the one currently favored, and it is the most violent. A binary star system, orbiting normally somewhere out in the galaxy, is deflected onto a path that takes it too close to the black hole. Tides pull the pair apart. One star is captured onto a tight, bound, eccentric orbit. The other is flung outward with the orbital energy of the pair added to it, at a speed high enough to leave the galaxy entirely. That mechanism was proposed by Jack Hills in the 1970s and 80s and applied to these stars in 2003 by Andy Gould and Alice Quillen. It is what the European Southern Observatory invoked for the new star. Their statement is that S301 was originally part of a binary that was torn apart by the black hole's tides, and that its companion was ejected fast enough to leave the Milky Way. Somewhere out there, at this moment, a star is coasting toward intergalactic space, and it left with the other half of an orbit we can still watch. And the mechanism has a second, independently observable consequence, which is the strongest thing going for it. If binaries are being torn apart at the galactic center, then for every star captured into a tight orbit, there should be another one leaving at enormous speed. Those ejected stars are called hypervelocity stars, and they exist. Astronomers have found them, stars moving fast enough to escape the Milky Way entirely, on trajectories that, traced backward, point at the center of the galaxy. The theory does not just explain the stars we can see, it predicts a population elsewhere, and the population is there. A fourth possibility appeared in a preprint in June 2026, and it is worth mentioning because it tries to unify everything. The proposal is that all of these stars, the disk and the S cluster alike, formed from a single episode of gas collapse, and that their orbits were later scrambled into the arrangement we see by the gravitational influence of an intermediate mass companion of around 10,000 solar masses. The candidate for that companion is the compact object sitting about 13/100ths of a parsec out, which has been argued over for years and may be the surviving core of an infalling cluster or a black hole of intermediate mass, or neither. If that proposal holds, then the migration explanation and the in situ explanation stop competing and become two parts of the same story. There is also a question nobody has closed about S2 itself. A study published in December 2025 ran 100,000 simulations with relativistic corrections to ask whether the best studied star at the galactic center could still be hiding a companion of its own. The answer is that it could, but only just. About 3% of plausible binary configurations survive both the dynamics of that environment and the current limits on detection. Which means that after 30 years of watching one star more closely than almost any other star in the sky, we cannot rule out that it is two. There is supporting evidence. A study published in 2024 showed that continuous binary disruption, combined with the slow reshuffling of orbits by gravitational encounters, reproduces both the observed distribution of eccentricities and a newly identified empty region where no S-star closest approaches are found. The mechanism predicts a gap, and the gap is there. A few more things worth knowing about this region. The gravity instrument achieves positional precision of 30 to 100 microarcseconds. The European Southern Observatory's comparison is the size of a car on the Moon. The upgraded version, completed in late 2025, with 4 laser guide stars fired over the mountaintop at Paranal, improved sensitivity by a factor of between 10 and 100. The new star was only findable because of that upgrade. It had been there the whole time, at that brightness, on that orbit, for the entire history of the field. The same collaboration has used S2's orbit to place a limit on any invisible mass hiding inside it. If there were a dense cusp of stellar remnants or dark matter concentrated around the black hole, it would perturb the orbit. There is room for no more than 3,000 solar masses of anything else inside S2's orbit, which is 0.1% of the black hole itself. The center is essentially just the black hole and the stars we can see. And in December 2024, Pulsar and colleagues reported something nobody expected to find there at all: a binary star system, 2 stars orbiting each other, surviving in the neighborhood of a supermassive black hole. It was detected from a periodic red and blue oscillation in its hydrogen emission as the 2 stars swung toward and away from us. It is estimated at 2.7 million years old, and it is predicted to merge into a single star within about 1 million years. Pulsar's own summary was that black holes are not as destructive as we thought. The same group has since suggested that detecting planets at the galactic center is now just a matter of time. To close the scale, the event horizon of this black hole is about 12 million kilometers across, which is roughly 0.08 of an astronomical unit. So the new star, at its closest approach, is around 150 horizon radii out. Close, in a way that lets us measure the shape of space-time. Not close enough to be in any danger. 100 or more stars, young enough to have formed within the span of the human genus, sitting in the single best measured environment in astrophysics, in the one place the physics says nothing can be born. Every explanation for them begins by saying that they came from somewhere else. The next entry on this list is a kind of star that theory says should exist, that has been searched for since 1975, and that has never once been confirmed. Number 2, the star with a dead heart. Number 2 is a star that may not be what people have claimed it is, in a category that may not have any members at all. Its designation is HV 2112. The HV stands for Harvard variable, and it earns that name honestly. It was first reported as a variable star in 1908 by Henrietta Leavitt in the course of the same Harvard photographic plate work that produced the period luminosity relation for Cepheid variables, which is the tool that later allowed the universe to be measured. So this star has been in the catalogues for 118 years. The reason anybody looked at it again is a paper published in 1975. The idea belongs to Kip Thorne and Anna Zitkoff, and it is one of the strangest objects ever proposed in stellar physics. Imagine a red supergiant. An enormous, cool, diffuse star, 1,000 times the radius of the Sun, its outer layers so thinly spread that they are closer to a laboratory vacuum than to air. Now imagine that at the very center of it, where the fusing core should be, there is instead a neutron star. Not a companion orbiting nearby. A core. One solar mass, 12 kilometers across, sitting at the middle of an object 1 billion times wider than itself. That is a Thorne-Zitkoff object. The models constrain it fairly tightly. A neutron core of about 1 solar mass, an envelope reaching around 1,000 solar radii, and a surface temperature near 2,700 Kelvin. Getting one is not as absurd as it sounds. Massive stars very often come in pairs. If one member of a pair goes supernova and leaves a neutron star behind, and the other later swells into a supergiant, the two can end up sharing a single envelope. The neutron star then finds itself moving through gas rather than vacuum, which means it feels drag. Drag drains orbital energy. It spirals inward. And if the process runs to completion, the neutron star arrives at the center and stays there. The star does not die when this happens. It keeps shining. But its energy no longer comes from fusion in a core. It comes from material settling onto a neutron star at the center of a supergiant, which is a genuinely alien way for a star to be powered. And here is the difficulty that has defined the entire 51-year search. From the outside, such an object would look almost exactly like an ordinary red supergiant. Thorne and Zitkoff said so themselves in 1977. The thing they proposed was, by its own design, nearly indistinguishable from something common. Almost. There is one signature, and it is chemical. In a massive version of these objects, with an envelope above roughly 14 solar masses, the energy is generated at the base of the envelope, right where it meets the neutron core, at temperatures and densities that permit a nuclear pathway called the interrupted rapid proton process. That process builds a distinctive set of elements, and because the whole envelope is convective, those elements should be carried all the way up to the surface where a spectrograph can see them. The predicted fingerprints are rubidium and molybdenum. Lithium is expected as well, produced by helium burning at the base of that same convective zone. The word interrupted in that process name is doing real work, and it explains why the fingerprint is what it is. In ordinary stars, heavy elements are built slowly, by nuclei capturing neutrons one at a time over thousands of years, with plenty of opportunity to decay into stability between captures. Near a neutron core, the conditions are different. Protons are captured rapidly, faster than the resulting unstable nuclei can decay. The chain runs up the chart of isotopes into territory that ordinary stellar burning never reaches. Then it stalls at particular nuclei with long decay times, and the products pile up there. Rubidium and molybdenum are where the pile-ups happen. They are not arbitrary markers. They are the specific places the process gets stuck. Theory also predicted rarity, perhaps 20 to 200 such objects in the entire Milky Way at any one moment. Out of 200 billion stars, that is 1 in a billion. There is a further constraint that narrows the target considerably, and it is worth knowing because it becomes important later. The envelope mass has to fall outside a particular range, either below about 8 solar masses or above about 14. In between, the models say the object is not stable and does not persist. So the search is not simply for a red supergiant with strange chemistry. It is for a red supergiant with strange chemistry and a mass in one of 2 specific windows. That common envelope phase deserves another sentence, because it is one of the more remarkable things in stellar physics, and it is not widely known. When 2 stars end up inside a shared atmosphere, the drag on their orbit is enormous, and the inward spiral is fast, months to a few years, not millions of years. The orbital energy released in that spiral is deposited directly into the envelope, and the usual outcome is that the envelope is ejected entirely, leaving a tight binary behind. Almost every close pair of compact objects in the universe is thought to have gone through one. The phase is brief, violent, and almost impossible to observe directly, because it is over before anyone could catch it. For a Thorne-Jitkoff object to form, that process has to go wrong in a specific way. The envelope has to survive. So the search became a search for chemistry. Look at red supergiants. Find one with too much rubidium. The candidate arrived in 2014, announced by Emily Levesque, Philip Massey, Anna Zitkoff, and Nydia Morel. Levesque had surveyed 24 red supergiants in our own galaxy from Apache Point, 16 in the Large Magellanic Cloud, and 22 in the small, using the 6.5-meter Magellan Clay telescope. 62 stars in total. One stood out. HV 2112 sits in the Small Magellanic Cloud, about 200,000 light-years away. A Voyager crossing takes about 3.5 billion years. It is spectral type M3, a cool supergiant at around 3,450 Kelvin, and photometrically it is violent. The Harvard catalog records a brightness swing of 4.8 magnitudes, a factor of about 80, on a cycle of roughly 600 days, with a distinctive double-peaked shape. The team's method was comparative rather than absolute. They measured the strengths of particular spectral lines relative to other lines and compared those ratios against the envelope defined by the other cool supergiants in the same galaxy. Anything falling outside 3 standard deviations of that envelope was flagged. On that basis, they reported excess rubidium, excess lithium, excess calcium, and excess molybdenum, and described the star as the first to display the distinctive chemical profile thought to be unique to these objects. One number from that survey is the honest headline, and it rarely gets quoted. 62 stars examined. One candidate. That ratio is not a failure. It is exactly what you would expect if these objects are as rare as theory says. But it also means the entire case rested, from the beginning, on a single object, and single objects are fragile. There is a symmetry in this story that is hard to miss. The star was first catalogued by Henrietta Leavitt, who worked at Harvard as one of a group of women hired to measure photographic plates, at a time when they were not permitted to operate the telescopes that made them. Leavitt measured the brightness of thousands of variable stars, and, in doing so, discovered the relationship between a Cepheids period and its true luminosity, which became the first reliable way to measure distance beyond our own galaxy. Everything in this video that depends on knowing how far away something is depends downstream on that. She catalogued this star in 1908 as one entry among many, and moved on. 106 years later, another woman's name appeared on the paper, claiming it was the strangest object in stellar physics. Anna Zitkov was a co-author on that paper. She had proposed the object in 1975 as a young researcher, working with Kip Thorne. 39 years later, her name appeared on the paper, announcing the first plausible candidate for the thing she had imagined. That is a long time to wait, and it is not the end of the wait. 12 years further on, it is still not confirmed, and the weight of the evidence has moved against it. 51 years is longer than most careers. It is not a tragedy, and it should not be told as one. It is simply the time scale on which a single question can stay open, and the person who asked it has had to hold it for all of that time. Because the candidacy has been challenged twice, and the two challenges are almost always conflated. They should not be. The first came in 2016, from Thomas Macarone and Selma de Mink. Using a proper motion catalogue, they measured how fast the star appears to move across the sky, and found a motion that, if the star really sits in the small Magellanic Cloud, implies a space velocity of about 3,000 kilometers per second. That is impossibly fast for a member of that galaxy, and it differed from Magellanic membership at about 4 standard deviations. Their proposal was that the star is not in the small Magellanic Cloud at all. It is a foreground star in the Milky Way's halo, of a known chemically peculiar type, polluted long ago by material from a companion that has since died. And that explanation had an attractive bonus. It accounted for the odd calcium ratio, because halo stars naturally have unusual calcium, and it accounted for the enormous brightness swing, because such stars pulsate that way routinely. Then Gaia arrived and defeated it. The data release. 2 proper motion places HV 2112 firmly in the small Magellanic Cloud, consistent with the original claim. The foreground argument was tested by a better instrument and did not survive. This matters for how the story gets told, because the popular version often credits Gaia with killing the candidacy. Gaia rescued it from the first challenge. The second challenge is the one that stands, and it came from a different direction entirely. In 2018, Emma Bisa, Ben Davies, and collaborators took a new spectrum with the Very Large Telescope and compared it against other late-type luminous stars in the same galaxy. They found no evidence for enhanced rubidium, no evidence for enhanced calcium, no evidence for enhanced potassium. Lithium does appear to be enriched, but lithium alone is not diagnostic. And by integrating the full spectral energy distribution from blue through mid-infrared, they revised the star's luminosity downward from about 105,000 solar luminosities to somewhere between 50 and 80,000, which pulls it below the range these objects are supposed to occupy. Their conclusion is that HV 2112 is most likely an intermediate mass star of around 5 solar masses on the thermally pulsing asymptotic giant branch. Which is to say, a large, old, unstable star of an entirely ordinary and well-understood kind. They also demonstrated something quietly damaging about the original evidence. The line ratios are internally inconsistent. Rubidium measured against nickel implies an excess of rubidium, but rubidium measured against iron is normal, and nickel measured against iron is also normal. Lithium measured against calcium and against potassium implies a lithium excess, while potassium measured against calcium implies no calcium excess. There is no single set of abundances that satisfies all of those ratios at once, which means at least some of them are being driven by something other than composition. In the same paper, Bisa's team nominated a replacement candidate, another small Magellanic Cloud star, apparently enriched in rubidium, though with no measurable lithium. That candidate has had its own reversals. Gaia's second data release raised the same foreground doubts about it that had been raised about the first star. Then, in November 2025, an analysis using the third data release concluded that it is very likely a genuine member of the Small Magellanic Cloud after all, with a local transverse velocity of about 52 kilometers per second. That figure is above the conventional threshold for a runaway star, which means it was thrown out of wherever it formed by something violent. Which is interesting, because forming one of these objects requires exactly that: a supernova, a surviving binary, and a great deal of violence. The authors of that paper are explicit that this does not prove anything about its nature. At number 9, we noted that the entire future of a magnetic helium star hangs on a mass measurement of 2.03 plus or minus 0.44, and that nobody can go and check. Here, that phrase arrives at full weight. The way to settle whether this star has a neutron star at its center is to look inside it. There is no instrument that does that, and there is no journey that gets there. The class has stayed empty for 51 years, not because nobody has tried, but because the object was designed by its own physics to be indistinguishable from something ordinary, at a distance of 200,000 light-years, through a shroud of its own dust, using only the light that reaches us. A survey published in 2020 is worth adding, because it reframes the whole search. Using automated light curves, a team identified 38 cool, luminous, extremely variable stars in the Magellanic Clouds, and 11 of them share the same distinctive double-peaked variability that made HV 2112 look special. Their derived masses run between 5 and 10 solar masses, which falls below the roughly 15 solar mass minimum theory requires for one of these objects to be stable. So that team proposes something else entirely, that these are super asymptotic, giant branch stars, caught in the middle of burning carbon, in a phase lasting only 10 to 70,000 years. If they are right, the search accidentally found the first identified population of a different rare object, which is not nothing. There is also an orphan fact that neither side has explained: the calcium. A theoretical analysis published alongside the original candidacy showed that a calcium overabundance is difficult to account for under either scenario, the exotic one or the ordinary one, and that fitting the other elements with an ordinary model required a finely tuned setup. Whichever explanation eventually wins, the calcium is still sitting there. Our own galaxy has a leading candidate too, a red supergiant in Sagittarius, and it is no less ambiguous than this one. But there is one genuinely promising route, proposed in 2025, and it does not involve looking at the star at all. If material is settling onto a neutron core at a rate above about a 10,000th of a solar mass per year, that accretion should produce neutrinos, of all flavors, with energies between 1 and 100 mega-electron volts. Neutrinos do not care about dust, or distance in the way light does, or about the 1,000 solar radii of gas in the way. And the calculation suggests that such a signal from the Small Magellanic Cloud would be within reach of the current and next generation of neutrino observatories. Which raises a strange possibility. The first confirmed Thorne-Zitkoff object might never be seen. It might be detected, instead, by particles passing straight through it and straight through the Earth, in a tank of water under a mountain. For completeness, the other messenger does not help here. The gravitational wave signature of such an object would only be within reach for a source in our own galaxy, and only for detectors that have not been built yet. And the deepest objection is not observational at all. Some theorists doubt that the merger can even work. The argument is that a neutron star spiraling into a supergiant's envelope deposits so much energy on the way in that the envelope is blown off before the core arrives. If that is right, the object cannot form, and the class is empty because it was never populated. There is one more open question, and it is a strange one to have about a class of object nobody has found. Nobody knows how they end. A paper published in 2018 is titled simply with the word explosions and takes on the problem of what happens when a Thorne-Zitkoff object runs out of envelope. The answer depends on details of the accretion physics that are themselves unresolved. And a review chapter published in 2024 surveys nearly 5 decades of work on the class, covering formation channels, stability conditions, chemical signatures and candidates, and ends without a confirmed example. That is a remarkable document to read, a comprehensive account of an entire field of study whose subject may not exist. So the honest position, stated plainly, there is no confirmed Thorne-Zitkoff object. 51 years after the prediction, 0 members. The one candidate that looked like a match is most likely an ordinary star of a familiar kind, and the 2 best remaining candidates are contested on grounds that will not be settled from here. That is a specific and uncomfortable place for a science to be in. The prediction is not wrong. It may simply be beyond what our instruments can test, which is a different problem and a harder one than being mistaken. 51 years, and the class is still empty, because the object was built by the physics to look like something ordinary. The last star on this list has the opposite problem. It has never looked like anything ordinary, not for a single night in 65 years. And it is close enough to see from a suburban back garden. Number 1. Przybylski's star. We have traveled a long way down this list. 200 light-years, then 3,000, then 20,000, then 160,000, then 200,000, and at number 5, 3.82 billion. Number 1 is 356 light-years away. It is the second nearest object on this entire list. Only the star we opened with, at number 10, is closer. And it is, by a considerable margin, the one we understand least. That is the shape of the finale, and it is worth naming before we begin. Everything we have looked at tonight has been hard to understand, partly because it is far away. This one is not far away. It is bright enough that a modest backyard telescope will show it to you tonight. It has been available to every instrument built in the last 65 years, for as many nights as anybody cared to spend on it. And the leading explanations for what it is include a companion nobody can find, an element nobody has ever made, and the possibility that several generations of careful people have been reading the lines wrong. It is catalogued as HD 101065 in the constellation Centaurus. Gaia puts it at 109.3 parsecs, which is 356 light-years, with an uncertainty of less than a single light-year. Older literature quotes 370. Its apparent magnitude is just under 8, invisible to the unaided eye, easy in a small telescope. Its surface temperature is around 6,300 Kelvin, a little hotter than the Sun. Its mass is about 1.4 solar masses, its radius about 1.9. At Voyager speed, the crossing takes about 6.3 million years. At 1% of the speed of light, which nobody knows how to build, 35,600 years. Agriculture is about 12,000 years old. Its spectral classification is contested, and the reason is that the spectrum breaks the classification scheme. It has been typed F0, peculiar, and F3, and G0, and catalog searches will return anything from B5 to G0 for the same object. One widely used designation appends the chemical symbol for holmium to indicate the peculiarity, which is a reasonable summary of the situation. Holmium is a rare earth metal that most people have never heard of, and that almost never shows up in a stellar spectrum at all. It was found in 1961 by Antoni Przybylski, a Polish-born astronomer working at Mount Stromlo Observatory in Australia. He published a short note in Nature under a title that already understates the problem: a G0 star with high metal content. Picture the moment, because it is worth sitting inside for a second. A spectrum of an 8th magnitude star in Centaurus is developing on a photographic plate at Mount Stromlo. The astronomer has classified hundreds of these. He knows what an F-type star looks like. There is a familiar comb of absorption lines, dominated by iron, a few dozen strong features he could name in the dark, with clean continuum between them. What comes up on this plate is a forest. The lines are packed so densely that in places the continuum barely shows through. And the strong iron lines that should be dominating the whole thing are weak. Whatever is making all those absorption features, it is not the elements that make absorption features in stars. He checks the plate. He checks the instrument. There is nothing wrong with either. The light that made that plate left the star around the year 1605. Before the telescope was invented, before the observatory, before the country in its present form, before anybody had drawn up a table of the elements at all. It crossed 356 light-years of empty space and landed on a piece of glass in Australia, and the man looking at it had no category to put it in. He wrote it up as a G0 star with high metal content, because that was the closest available description. 65 years later, there is still no better one. There is a small footnote to that paper that is almost too neat. For years, it was effectively invisible to literature searchers because Przybylski's surname was misspelled in the record. The star that broke the periodic table was hard to look up. Then, in 1978, the star produced a second discovery. Don Kurtz pointed a photometer at it and found that it pulsates. The period is 12.15 minutes, and the amplitude is about 1/100th of a magnitude, which sounds tiny and is in fact obvious. He had it within half an hour of observing. That made this the first rapidly oscillating peculiar A star ever found, and it founded an entire class of object. It also demolished a belief that had been standard until then. Chemically peculiar stars have very stable atmospheres, and stability was assumed to be incompatible with pulsation. This star does both. The class now has many members, all pulsing in high overtone acoustic modes with periods between roughly 6 and 24 minutes. This one sits near the fast end. Now the chemistry, and it matters enormously that we separate what is solid from what is not, because this is a star that attracts extraordinary claims, and the value of tonight's account depends on getting the boundary right. Here is what is solid. A comprehensive analysis published in the year 2000 derived abundances for 54 elements. Iron and nickel are deficient by about a factor of 10. Deficient, not absent. That distinction matters and gets lost constantly. Cobalt is enhanced by roughly a factor of 30. And the lanthanides, the rare earth elements, broadly follow the same relative pattern they have in the Sun, but are enhanced by 3 to 4 orders of magnitude. 1,000 to 10,000 times more holmium, dysprosium, neodymium and erbium than the Sun contains. Elements with odd atomic numbers are systematically less abundant than their even-numbered neighbors, which is a pattern with a known nuclear origin. And more than half of the spectral lines in this star's spectrum have never been identified at all. That last fact is going to matter a great deal in a moment. The magnetic field is strong. A longitudinal field of up to -2.5 kilogauss was measured in 1976, revised to about -1,567 Gauss in 2008. And the rotation may be extraordinary, with a caution attached that the original authors put there themselves. A paper published in 2018 fitted a sine wave to 43 years of magnetic field measurements, assuming a simple dipole geometry, and derived a rotation period of about 188 years. If that is right, this star turns once every 2 human lifetimes. But the authors state explicitly that it is not a unique solution and requires future verification, and this video is not going to state it more confidently than the people who published it. The same paper did establish something genuinely new. Using the way praseodymium and neodymium are layered at different depths in the atmosphere, they demonstrated the presence of a radial magnetic field gradient, the first time that had been shown for any star. Now the contested part. In 2008, a group led by V. F. Gopka and A. V. Yushchenko published identifications of absorption lines from short-lived actinides in this star's spectrum, working from a high-resolution spectrum taken with an 8-meter telescope. The list of elements they claimed is remarkable. Actinium, protactinium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium. In fact, lines from every element between atomic number 84 and 99, with the exception of astatine and francium. Take einsteinium alone, because it is the one that makes the point. Einsteinium does not occur naturally on Earth. It was first identified in the debris of a thermonuclear weapons test in 1952. Its longest-lived isotope has a half-life of about 472 days. If there is einsteinium in a stellar atmosphere, it was made there, recently, and is being replenished continuously. So what is the status of that work? It has never been independently confirmed. It has attracted remarkably little follow-up in the 18 years since. And before any exotic mechanism was proposed to explain it, the working assumption in the field was that the identifications were simply erroneous, because short-lived actinides in a stellar atmosphere seemed impossible. The strongest reason for caution is not theoretical. It is mechanical. This is one of the most crowded stellar spectra ever recorded. More than half of its lines are unidentified. In a spectrum like that, identifying a weak feature means claiming that a particular dip in a forest of overlapping dips belongs to one specific element and not to some blend of others. That is exactly the kind of measurement that goes wrong, and everybody involved knows it. Promethium is the sharpest test case, and it has been tested. Promethium has no stable isotopes at all. Its longest-lived is promethium-145, with a half-life of 17.7 years. Any promethium sitting in a stellar atmosphere would have to be being manufactured right now, at the surface, continuously. Charles Cowley, who became the central figure in the study of this star, wrote a line about it that has been quoted ever since. The spectroscopic evidence, he said, is strong enough that we would declare promethium to be present without hesitation if any of its isotopes were stable. But Cowley's own analysis in the year 2000 found no support for either promethium or technetium. A paper in 2004 then claimed detections of both. And the most recent word came in 2023, when a dedicated reanalysis of 3 promethium lines concluded that almost all of them are heavily blended, and that at present it is impossible to definitely claim the presence of this element in the star's atmosphere. A companion paper synthesized the technetium resonance line, found it simply not visible, and reduced technetium to an upper limit. So the honest summary is this. The rare earth enrichment is solid. The iron and nickel deficits are solid. The magnetic field, the 12-minute pulsation, the unidentified forest of lines, all solid. The actinide identifications and the promethium are a single team's claims in an extraordinarily blended spectrum, and the two most recent dedicated reanalyses failed to confirm them. That is where the evidence actually stands. Which does not make the star less strange. It makes it strange in a more interesting way, because the four candidate explanations are still on the table and every one of them has a serious problem. The first is a hidden neutron star. If this star has a compact companion bombarding its surface with gamma rays and free neutrons, heavy nuclei could be manufactured directly in the atmosphere by nuclear reactions. That was Gopka's proposal, and it would explain everything at once. Jason Wright at Penn State considers it effectively ruled out. The star's spectral lines are sharp, which allows precise velocity measurements, and those measurements show no short-period companion. There is no ultraviolet excess and no X-ray excess, and a neutron star close enough to be doing this would produce both. The second is the island of stability. In 2017, Vladimir Dzhuba, Victor Flambaum, and John Webb at the University of New South Wales published a proposal that the short-lived actinides are decay products of a long-lived, metastable super-heavy nucleus, one sitting at the magic neutron number 184, where nuclear structure theory predicts an island of relative stability among elements far beyond uranium. Their candidate parents sit around atomic numbers 114, 120, and 126, possibly seeded into the star's birth cloud by a nearby supernova. They did the responsible thing and computed the expected isotope shifts, so observers would know where to look. No such nucleus has ever been made in a laboratory. The heaviest elements ever synthesized on Earth survive for milliseconds. The third is the mainstream explanation, and it is the one most stellar physicists actually hold. It is called diffusion and radiative levitation, and it works like this. In a star with a strong magnetic field and no surface convection, the atmosphere is extremely still. Nothing is stirring it. Under those conditions, individual elements begin to sort themselves out. Gravity pulls everything down. But radiation streaming outward pushes on atoms, and how hard it pushes depends on how many spectral lines that particular element has at the wavelengths where the light is brightest. Elements with dense line forests, like the rare earths, get pushed hard and float upward. Elements that absorb less efficiently sink. Over time, the surface composition becomes a sorting artifact. It tells you almost nothing about what the star is made of overall, and nothing whatsoever about what its core is producing. This explains the rare earths beautifully. It explains the iron and nickel deficits. It is why chemically peculiar stars exist as a class at all, and there are more than 8,000 of them in the catalogues. What it does not explain is an element with a half-life of 17 years. Diffusion sorts what is already there. It does not create anything. And that is precisely why the anomaly, if it is real, matters. Which leaves the fourth explanation, and it is the one the most recent work supports. The lines were misread. There is a piece of history around this star that has to be handled carefully, and this video is going to handle it plainly. In 1980, a paper was published proposing that if a technological civilization somewhere were disposing of nuclear waste by dropping it into a star, the resulting spectrum would be detectable, and it predicted that such a signature would show up specifically in late A-type stars. Przybylski's star is a late A or early F peculiar star. That is an accidental fulfillment of a prediction, and it is why this object keeps reappearing in discussions of technosignatures. It is also why the honest framing matters more here than anywhere else on this list. A prediction being accidentally matched by an unrelated anomaly is not evidence. It is a coincidence with a citation attached. The most recent dedicated work on the actinide lines could not confirm them, and the mainstream diffusion explanation accounts for everything that is solidly established. The idea has an older pedigree still. In 1966, Carl Sagan and Iosif Shklovsky relayed a suggestion that a civilization might deliberately salt its own star with a short-lived isotope as a beacon, precisely because such an isotope has no business being there. And they noted the difficulty immediately. Technetium, which also has no stable isotopes, had already been found in ordinary stellar spectra, where it is produced by perfectly natural processes. The ambiguity was identified before the case arose. And there is a genuine precedent that cuts the other way, which is worth keeping in mind. Helium was discovered in the Sun before it was found on Earth. Finding a new element in a stellar spectrum first is not unprecedented, and dismissing an unexpected line as impossible has been wrong before. It is worth stressing that this star is not a one-off freak sitting outside every category. It is the extreme tail of a real and well-populated class. The catalogue of chemically peculiar stars lists more than 8,000 entries, and the magnetic ones form the largest subgroup within it. Plenty of them have rare earth enhancements. Plenty of them have suppressed iron. What distinguishes this one is degree. It is further out along every axis than anything else in the catalogue, far enough that the explanations which work comfortably for the rest start to strain. And the strangeness is spreading rather than contracting. Another peculiar star in Perseus is now under investigation for unstable radioactive elements in its upper atmosphere. A separate extreme case has a claimed confident detection of doubly ionized thorium, which is a long-lived actinide and therefore far less contentious, but which nobody expected to see either. There is a paper from 2023 searching this star specifically for deuterium. The hunt for anomalies here has moved well beyond the actinides, and a review article published earlier this year is titled, accurately, "Still Bizarre After All These Years." The pulsations have been put to work as well in one of the more elegant applications of this star. Because the oscillation frequencies depend on the interior structure, they can be used to constrain properties that are otherwise inaccessible. An astroseismic model built from the observed frequency spacing of 64.07 microhertz returned a best-fit mass of 1.5 solar masses and a polar magnetic field strength of about 9 kilogauss. That was one of the first times a magnetic field had been determined astroseismically for a star of this class. The same model returned an age of around 1.6 billion years, and that number should be treated as contested because other work has quoted ages of tens of millions of years for the same object. Even the star's age is unsettled, which is, in a way, the fitting summary. We have measured this star's chemistry to 54 elements, its pulsation to the second, its magnetic field along the line of sight, and now its gradient with depth, and we cannot agree on how old it is, how fast it turns, or what half of the lines in its spectrum belong to. Two people, finally, because this star has consumed careers. Antony Przybylski found it in 1961 and had no category for it. In 1964, Charles Cowley wrote to ask him how his name was pronounced, and was told the initial letter is almost silent. Cowley spent decades on this star. He wrote the definitive abundance analysis. He wrote the line about promethium that everybody quotes. He argued about it, in print, with almost everybody who worked on it. He died in 2024, and it is still unexplained. At the very beginning of this list, we said that the light is the only thing that ever makes the trip. It was a limitation then, a way of describing distance. It is the whole foundation now. Every claim about this star, every element on that contested list, every argument about neutron stars and super-heavy nuclei and radiative levitation rests on light. There is no sample. There has never been a sample. There will never be a sample. The light that made Przybylski's photographic plate in 1961 left the star around 1605. The light arriving tonight left around 1670. And at the very best speed anyone can seriously imagine building, the journey there takes 3 times longer than recorded history. So we come to the end of the list where we began, more or less, in terms of distance. 10 stars, none of them reachable, ranked by how much of each one the mystery had eaten. It started with a single number attached to an ordinary star. It ended with an entire surface that nobody can account for, on a star close enough to find with a garden telescope on a clear night. Proximity bought us nothing. 65 years of unlimited access to an 8th magnitude star has produced a forest of lines, half of them unnamed, and 4 explanations that all have holes in them. Somewhere in Centaurus tonight, that star is turning once every 2 centuries, pulsing every 12 minutes, and doing whatever it is doing, exactly as it has been for as long as anyone has watched. We will not go there. The light will keep arriving anyway. Sleep well, and good night.